Hi everyone, I'm Prashant Ratanchandani and I'm the VP of Engineering for the Family of Apps Foundation Engineering team at Meta. I joined Meta a little over 5 years ago and I now support the team which powers our messaging, calling, mobile, and web platform for the company. So as you can imagine, building for mobile at scale is very near and dear to my heart. For several years now, we've run these at-scale conferences to bring together some of the smartest people who work on some of the most challenging problems we face as an industry. And today I'm genuinely delighted to welcome each and every one of you to this latest edition of Mobile at Scale. Your presence here today is a testament to our collective dedication to shaping the future of mobile apps. Thank you so much for joining us. Mobile at Scale started at a very different time for our industry, well over 10 years ago. Meta and the industry at large was grappling with the shift from web to mobile development and racing to build apps to capitalize on the phone. I don't think we fully recognized at the time how rapid and transformative this evolution would be. This little device in our pocket has woven itself into the very fabric of our daily lives. It's changed how we communicate, it's changed how we work, and how we play. It would be easy for me to reflect on this disruption just from the lens of Meta. I think the story of the mobile apps we built here are well known, whether it's Facebook, Messenger, Instagram, or WhatsApp. Apps that over 3.8 billion people use every month and over 3 billion use every day. But all I had to do was open my home screen this morning to see everything. From my reading app from the library, an app to control the temperature in my house, my professional profile on LinkedIn, and yes, even my kid's favorite pizza joint. Mobile is our heartbeat. It's as relevant as ever. It's not just a device in our pockets. It's a gateway to innovation, a conduit for connection, and even a platform for progress. This edition of the conference is timely, given the ever-shifting zeitgeist of mobile development. Our journey, like I said, began in the early days of mobile, where our collective mission was clear. We had to build quickly. We had to seize the moment as smartphones took the world by storm. I liken it to a gold rush as everyone raced against the clock to stake their claim in the app landscape. Increasingly, we shifted to an area of optimization, a phase where we grappled with the complexity of a fragmented device landscape. We navigated the labyrinth of lower-end devices and networks, honing our craft to deliver experience to users across the spectrum. It was a period of fine-tuning, of adaptation, where we learned to thrive together amid this diversity. But through it all, we kept launching new products and experiences to keep things relevant and interesting. Some things have stayed true, however. When I look back on this evolution, things have been constant. For me, quality has always been at the forefront. Ultimately, even as we iterate and build these new experiences, they've come to expect the basics. The experience has to be fast. The experience has to be reliable. And their expectations on craftsmanship in our design and intuitiveness of our product, they are ever rising. And we need to continue to move faster than ever before. Look, not a single day goes by when we're not challenged by a new trend. This new trend is sometimes the risk of a new means of communication, such as community chats or broadcast channels, or the rise of a new sharing format, such as short-form video, which took the world by storm. And sometimes it's rising expectations on privacy or end-to-end encryption for messaging apps. In all these cases, what has defined mobile has been our ability to move fast and iterate quickly. To do this, we've unlocked innovation in shared systems like UI frameworks and data frameworks like GraphQL, which was built at Meta. We've built build systems for ever-growing code bases. We've even changed programming models and even the language that we use with the rise of Kotlin and Swift. This is well reflected in our agenda today. We're going to hear from some of the people building some of the most complex experiences at scale, whether that's the messaging infrastructure that powers messaging across Meta, and how we iterate quickly using design systems that scale. We'll continue to see how we're pushing forward on iterating faster, from both how we literally build the Instagram app and how experimentation unlocks moving fast at Instacart. And at a time when many think the industry is not launching anything new anymore, I'm excited to hear about our newest 0 to 1 app in Threads from within Meta, where we landed a new experience for people at breakneck speed. But of course, you know the biggest disruption our industry has seen in a while is upon us. For those of you that tuned into Meta Connect or have been following the innovation from OpenAI, this is the era of generative AI. This is a remarkable evolution, a technology that has the potential to become a core part of the mobile app experience in the years to come. Generative AI is not just about automating tasks, it's about enhancing the user experience. We want to make our mobile apps smarter and push the boundaries of what's possible. In many ways, when I model our work on mobile over the past many years, I think about Maslow's hierarchy of needs. If you're not familiar with this, it's where you need to meet the base needs for a human first. You need to have the physiological needs like food and water met, and security and safety, before you can talk of esteem and self actualization. Our work on the fundamentals and quality is at the base of the pyramid of mobile apps. It's what everything depends on. They first need to work, they need to be consistent in terms of quality, and then we can talk about enabling delight. But I genuinely believe we are now entering that era of delight. And generative AI could change the way we've enabled these experiences in the coming years and take us there. With that, it's time for action. I'm thrilled to introduce our keynote speaker, Mohsen Aksen, who will kick us off with how to think about generative AI for mobile apps. Mohsen, over to you. Let's get started on this adventure together. Welcome again to Mobile at Scale.
Generative AI and mobile application development are not two things that you tend to think about together. Today, we are here to talk about the intersection of these two worlds and to talk about how this phenomena of generative AI is going to meaningfully intersect our world of mobile software application development and, in the process, make us better engineers and help us build better products. I'm Mohsen Aksen. I've been at Meta for 7.5 years. I have worked on messaging products, mobile applications, and I've worked on AI products, including generative AI. And it's my pleasure to take you on this journey with us today. You've probably heard about generative AI. I assume everyone has heard about it for now. And I think there's many ways for us to think about it. We draw it as a cross, a kind of fork in the road, but we can think about it in a few different ways. We can just ignore it, assume it's not relevant. It's kind of the server thing. We can think about it as a threat and get hyped up about like a lot of the safety concerns, a lot of the job debate. We'll talk about that. Or we can think about it as an opportunity. I think we are here to talk about it as an opportunity. We will be respectful and aware of its challenges, and we will discuss those as well. So we will apply learnings from our own organization at Meta so that we all, as mobile engineers, can use generative AI in an effective way to move to the future. Our industry has had a great deal of paradigm shifts over the last 50 or 60 years since the invention of computers. We've seen large computers and taking floors and going all the way down to being in our pockets or in our ears. We've seen the rise of the internet redefining what software is. And these paradigm shifts bring a lot of uncertainty and a lot of change. We believe we're at the beginning of one of these paradigm shifts, and we believe it is powered by generative AI. And we believe that it will lead to kind of a new ways for us to interact with computers, with technology. And also it will lead to new ways for us to think about our careers as software engineers. So what's generative AI? Well, the story started with transformers. Transformers are, a branch of deep learning networks, and they are trained on very large amounts of data. These transformers effectively, they read a lot of data and they figure out relationships between things, between words, between sentences, between contexts. And as a result, they have an emergent ability to be able to complete what you give them and effectively attempt to use their knowledge, use that training, use that network to, I'm going to use the word invent. We will talk about that in a little bit more, invent or generate the remaining context. We will see examples of that. So they've been used very effectively in things like translation models. As a matter of fact, that was the initial use case for generative AI. They've been used in image generation. You sometimes will hear about those being talked about as diffusion models. The flagship of transformers are probably so-called large language models. These are specific types of transformers that are trained on trillions of tokens. And these are the ones that do precisely what I just described. They read an enormous amount of text. And you're able to give them a small amount of text, and they're able to take that text and effectively complete it, generate what comes next. They could be fairly brilliant at creating content. They can create a lot of different things. With a small piece of text, you can have a large language model create emails or stories or comments. Their siblings, the image models, can take a small piece of text and generate an entire image, an entire scene. They can generate a sticker. We will talk about that when we talk about Meta launches. In the example here, we talk about a very small sentence of telling the language model, generate a Python program for A-star pathfinding. And what you saw is the language model produced the Python code and produced test code. Now, it's easy to assume it just memorized that. It just saw that exact question with the exact response. Well, if you ask the language model to try it differently or to structure the code differently or to produce different tests, you will see that the result is very different with the same exact result. What you're seeing is I'm capturing an intent with text. The language model is trying to satisfy that intent, in this particular case, by producing code, by producing tests. So you can now start thinking about them as kind of these universal computers, effectively. You can think about them as intent-based computers, if you wish. In the example here, we use a few examples to get the language model to think about itself as a classifier of sentiment. So you give it an example, a positive example, a negative example, and kind of you get it to try and guess what should be the next example, and you will see that it was effective. At least based on that pattern, it probably matches the intuition of most humans of, okay, well, that probably means neutral. It's not clear which way you classify. So language models are not things you always just give text in and get text out. Sometimes you can instruct them, and actually I would say often, as software engineers, you will instruct them in a way where you take user input, you'll do some work on it, you give it to the language model, and you instruct the language model to give you some structured data. They might give you SQL queries. They might give you JSON data. They might give you YAML data. They might call APIs that you implement. You process them. You may take the results and produce user experience, or you may take the result and give it back to the language model. We will discuss that in a few examples later on. But fundamentally, they are still text in, text out, although you can play these tricks to get them to give you different kinds of text, structured text, that you can take real structured actions with. While they're amazing generators of content, large language models do have challenges. One of the challenges is their training cutoff. They are trained by information up to a certain point. They do not have a built-in ability to get real-time information. And that severely limits them. In the example we show, that's a language model that was asked about stock price. You can ask it about weather. You might have internal data. It has no idea what these things are. It was not trained with them. It was not fine-tuned with them. So it doesn't have access to that data. So that's one of the challenges. The more serious challenge is because they're such effective creators, they're generators after all, when they don't know the answer, sometimes they'll just invent an answer. And as a result, they can appear to hallucinate. They can appear to have flawed logic. The example here, we show it as an example where most people would hope would figure it out pretty quickly. And a very advanced large language model might struggle with that. So now you can look at these language models and you can say, well, you can dismiss them. What's the value of something that I guess is kind of interesting, can generate content, and it doesn't have access to real-time information, and it can invent stuff. Does that mean it is only limited to creative writing, creative use cases? I don't think so. And I think it's very important that we do not underestimate them. It's important that we don't dismiss them as, well, they're just for creative writing. They're not really for real software. The reason is simple. The industry is fixing these problems. People are clever. And the industry keeps figuring out solutions to these problems. The problem of hallucination can be mitigated, can be addressed through a very large number of techniques. I'm not going to talk about the very advanced ones like fine-tuning, etc. But instruction prompting and picking very specific instructions to manage the language model and have it to produce the output that you desire, giving it examples seems to make a difference. Sometimes asking it to question itself and review its process dramatically improves its reasoning ability. On the up-to-date information side, we've learned how to get the language model to say, I don't have that data. I'm going to tell you I don't have that data, what I need, and you give it to me. And then you can, so effectively you give the language model text, it comes back to you as something structured. You go execute, and you give it the data, and then it responds. You will hear these things called about as different patterns. You hear them talk about as tools, plugins, functions, retrievers. They're all in the same vein. They're all ways for software systems to augment large language models, enable them to have access to real-time information. At Connect last week, I believe, or the week before, we introduced Meta AI, and Meta AI has the ability to search the web. And the way Meta AI does that, it knows when it takes a user request, whether it has the knowledge to satisfy it. And when it doesn't, it talks to us, and we talk to a search engine, we get the results, we give it to the language model, and the language model responds. So let's not assume that all is lost, that these large language models are just creative writing tools, clever, haiku generators, and things like that. They are far more capable than that, and the industry is working hard to address them. Now you can also flip to the other side saying, oh my God, okay, well, they can create code. We're fixing precision. We're giving them access to real-time information. And because of that, you can start thinking about them as a threat. You can think about them as a safety threat, and you can think about them as a job security threat. From a safety perspective, we'll talk about that more. From a job security perspective, if these things can actually code and debug and profile and analyze logs and do a lot of things that we do, could they take away our jobs as software engineers? I think we're here to say no. All of us, not just myself. If you think about senior engineers in the industry, they tend to write less code. They tend to look for harder problems, and they tend not to take on a lot of the manual coding tasks. They leave that to more junior engineers. So one way to think about the arrival of AI and large language models and generative AI into the world of software development is, instead of a replacement for software engineers, we should think about that as an accelerator for software engineers. It just accelerates our tenure more rapidly because it can take on a lot of the tasks that used to take us time and used to take us a lot of learning. And instead of thinking about them taking our jobs, they're more of an opportunity for us to up-level our jobs. Let's solve bigger problems. Let's solve harder problems. Let's think about, again, a lot of what senior engineers do in organizations. They think about processes. They think about architecture. They think about algorithms. They think about code. They think about the structure of systems. They think about, testing. They think about experience. They become more multidimensional. And I think the arrival of AI as an assistive technology in coding should accelerate all of us into that tenure. So as programmers, we finally are getting something that we've always wanted. We're getting a programming assistant. And we've talked about this actually for decades, about the dream of having the tools and the systems we use understand our intent and help us in more fundamental ways. We have been on this journey, and generative AI could be the pinnacle or like the beginning of a dramatic shift in that journey. We now have generative AI models that are specializing in code generation, help us produce better code. CodeLlama, released by us a few weeks back, released by Meta, is a great example of that. Some of you might have used GitHub Copilot. Some of you might have used OpenAI to generate code. They can do more than just generate code. The AI can play an adversarial role with you. Maybe you write the code and the AI can write the tests, or you write the code and the AI writes the tests. It can help you figure things out. If you're seeing cryptic error messages and you can't figure out, you could probably paste the code and the error message, and the AI could be almost like having another programmer, a fresh pair of eyes to look at things and help you. So I think a great way for us to approach the generative AI problem from a software development perspective is to think about us as software engineers being challenged to uplevel our skills and have an amazing set of tools now that can truly make our experience more effective and more productive. So it is an opportunity for us to be better software engineers. Equally, if not more importantly, it can help us build better products. The world of software always evolves in complexity, and a task as simple as scheduling an appointment becomes a very large set of UI experiences. Those of you who've gone through like settings in products or privacy, or again, we use an example of scheduling an appointment, the amount of user experience that we have to develop, we have to refine, and the user has to interact with is quite large. And I think that's there with reason. It probably will be there for a long time with reason, but we can augment it and offer users an easier way to interact with these complex forms. So maybe instead of the user clicking every button and filling out every form, they have the option to say a sentence and have the AI fill out the form for the user to then complete the task. And maybe in more advanced universe, the AI can actually complete the task. So it is probably easier to say, schedule a team meeting on Wednesday at 2 p.m. Let's repeat that every 3 weeks, except on, if it overlaps with something. And remind me 15 minutes before. And it can fill out the form for a user, and the user can just submit it. In addition, it can help us build products that require less screen time. Some products demand screen time. They deserve it. They're entertainment products, etc. Some products we at least have the option to allow the user to look away from the screen and still use our product, interact with our technology. They might be able to talk to our software, and our software might be able to talk back to the user. That's another kind of opportunity that large language models and AIs can play a role in our applications. Not taking away the screen, maybe reducing the screen and playing a complementary role. Insight is a tricky topic that we struggle with often. We help users with onboarding and with tool tips and with tutorials and with walkthroughs and with external documentation. and with all sorts of guidance and like YouTube videos and all sorts of things, and they will always be with us. But the AI can come and play and kind of a complementary role to all that world and help software teach the user, suggest to the user what to do next, have an additional insight on what the user, help the user onboard, help the user make some changes that might not be very obvious or very intuitive for most people. So AI can help make us better engineers, and it can help us build better products. Let's talk about these large language models and where we get them and how we use them. I will talk about Llama 2 as I am of Meta. Large language models come in a variety of sizes and flavors. Generally, smaller models tend to be cheaper to operate and run faster. So the inference speed, when the time you give it text, the time you get text back is going to be faster. And therefore, it tends to be cheaper. You're using less GPUs. Their quality might not be as good. And quality is a subjective measure. You're going to have to decide what you mean by quality. It might mean the brevity of the response if you want the AI to respond in a concise way. It might be the tone of the response. It might be the sentiment that it actually classified based on your request. It might be the task that it had to do if it was an assistant supposed to produce an API call that performed a particular task. In general, you will find that the larger models are more capable in quality without having to do advanced machine learning techniques like fine-tuning. Smaller models are less capable, but are cheaper. So you will have to learn and you'll have to experiment to figure out what works and what doesn't work for your domain. In terms of actually integrating with them, nothing could be simpler. If assuming that you have a hosted version of one of these large language models, you're probably going to be dealing with usually one or two very simple APIs. You give the model a piece of text and it gives you back text. This is what we call a text completion. You see the example here, the color of the sky is, and it's going to complete it with blue. Actually, if you try this on some language models, you will see that it's answering with a lot more than blue. We will talk about that a little bit. The second topic is you can use them in what we call chat completion. Chat completion is like a more sophisticated version of text completion where you role play with the AI. You give it examples of what the user would say and how it should respond, and then you give it user input and then it responds. So it's a lot more commonly used in what we call chatbots, in what everyone calls chatbots. So text completion completes sentences. Chat completion gives you a more interactive experience between you and the AI, but it literally couldn't be simpler than that. They're very, very simple systems. They're complex on the inside. They're very simple on the outside. So now you can say, well, okay, well, they're very easy. I'm just going to go right to it and I want to do it. Well, hold on. Just be careful. Let's go back to the topic of safety. These are very powerful systems. These are systems that have read an enormous amount of content, have learned a lot of things, and not a single human has read every single thing they've read and curated it and double-checked it. So they're also prone to hallucination. So it's very important that you take safety in mind. So you have to basically watch out for users potentially exploiting these models and getting them to do things or answer things they should not be answering. You have to watch out for the model either hallucinating or leaking information out of its knowledge that you really don't want to expose to your users. And you also really want to watch out if the language model is going to give you structured data that you're going to act upon, an API call, a database query. You have to be really careful with these things. Those do raise legitimate safety concerns. When we released Llama 2, we released two documents. One is a research paper that talked a lot about what we did for safety in these Llama models. The second one was we created a responsible use guide. I strongly encourage you to explore both because they talk a lot about this topic, how you validate input, how you validate output, how you protect your systems when you integrate AI into them. These are possible. A lot of companies are doing that, and I encourage you to consider that. Token limits and context window is just a quick reminder that language models are effectively stateless servers. You give them data and they give you output and they do not remember. You have to give them more data for them to remember and more data for them to remember. And eventually they run out of what we call a context window. So you have to look online, you have to read, you have to learn how you can address these limitations of memory and context window. You can be effective if you've seen examples of some of the chatbots, and we'll talk about a couple of them in a minute. They have the illusion of memory, and they actually have some memory, and we will talk about that briefly. So at Meta, we have obviously embraced this phenomena. Many years ago, I was drawn to Meta because it was a flagship AI company, and I'm proud to say that we've continued to be a flagship AI company. We have embraced the generative AI paradigm shift wholeheartedly. We have released these world-class models. We have released these world-class code generation models. And a couple of weeks back, we released a suite of enhancements to our products that are all AI powered. We are giving our users the ability to not just consume stickers, but create stickers by using creative language models or creative diffusion models. We've given them the ability to produce images by imagining things typing in text and having our AIs give them images that they can share with chat members and friends and family. We've given them a Meta AI assistant, which is a general purpose AI that can almost is open-ended. You can use it for anything. And that AI assistant has access to search, so it's able to get real-time information. It has a tremendous amount of knowledge and memory. You can ask it questions. You can ask it about real-time information, about historical information, about insight. You can give it instructions. You can ask it kind of to do things or of how to do things, and it can teach you how to do things. And finally, we've created these very interesting AI characters that we put into our products that can help people with travel, with cooking, with advice, with entertainment, with gaming, with sports, with health, with all sorts of things. You're seeing the beginning of us now starting to use AI in an effective way to build better products. This is all an external view, and you're seeing Meta take generative AI very seriously, both from a model perspective as well as a product perspective. But I'm here to also tell you we've taken it to heart also internally. We are big believers in the power of generative AI to help us all be better engineers, to help us be more productive, to have higher quality software, faster time to market, less issues. We're not spending time thinking about whether it's going to replace us or not. We're spending more time thinking about how it can make us better, how it can empower us to be better engineers. And we're all, like everyone else, we're all still early in that journey, but we're fairly confident generative AI is going to play a very key role in our ability to perform as software engineers in the future. So with all of that in mind, I would strongly encourage you to think about the paradigm. Do not ignore generative AI. Do not dismiss it as a gimmick, but also don't just plug it in and just YOLO. Think about a thoughtful, responsible way for you to use it in your products, improving your products and your experiences. Also, please do not just simply dismiss it as a job threat, and think of it more as the next generation of tools that can help all of us be better engineers. And I do think that generative AI will be with us for quite a while. So we might as well all go on this journey together and grow together and enjoy the process. Thank you very much.
Hello, everyone, and welcome to the very first Mobile at Scale conference. I'm Parisa Zaire, a technical PM at Meta, and I'm thrilled to be your host for today's exciting journey into the world of mobile development at scale. First, a big thank you to Mohsen for that captivating keynote on Gen AI, and a big shout out to Prashant for kicking us off. Today, we're diving deep into the fascinating realm of mobile development, where we'll explore the challenges, innovations, and breakthroughs that come up with scaling up our mobile apps. We've gathered some incredible speakers to share their insights and experiences with you, and I cannot wait to introduce them to you. So fasten your seatbelts because we're about to embark on an incredible journey of discovery and learning. Let's get started. Throughout today's presentations, we'll explore different aspects of mobile development in 3 main sections. In the first section, we'll talk about creating a dynamic messaging platform, improving IG build speeds, and explore Kotlin at Instagram. Then we'll take a short break before the second session, which includes the making and launching of Meta's latest app, Threads, followed by a panel on React Native with some industry leaders. Finally, after a lunch break, we will close out with a talk from Instacart and cover Meta design systems at scale. Thank you for being here today. If you have any questions or ideas for future at-scale events or Meta Tech blogs, you can visit our website at @scaleconference.com or scan the QR code on the screen. To kickstart our presentations today, I'm thrilled to introduce messaging at scale. Messaging is something we all use every day, and when you think about how Meta's Facebook and Messenger apps connect more than 1 billion people so smoothly, you can see that managing the issues that come up with such a massive mobile app is quite challenging. Join us for an enlightening journey with Meta software engineer Akshay Patel, who will talk about the challenges of creating a dynamic mobile messaging platform. Akshay will discuss design models, their strengths and limitations, and how Meta's mobile messaging system, MSIS, was carefully built with these ideas in mind. You'll also learn about MSIS's ability to grow and work well with other apps. Enjoy!
Hi everyone, I'm Akshay and I'm a software engineer for the messaging client platform team here at Meta. Today, I'm going to take you on the journey of building a mobile messaging platform. More particularly, I'm going to talk about how we solve for the dynamic of agility versus efficiency when operating a platform at our scale. As a social media company, it should come as no surprise to anyone that messaging is everywhere. You see it clearly in our inbox apps like Messenger and WhatsApp, but it may be not so much in your face when you look at our feed apps like Facebook and Instagram. But messaging is more than just a simple inbox and some chats. You use it when sharing a reel with some friends on Instagram. You also use it when replying to a story on Facebook. Of course, most people know Meta for its consumer apps, but messaging is also a critical part of Meta's business offerings, like workplace chat and business inbox in Messenger. It can be hard to keep track of all the messaging features that we have in all of these apps. As a developer, things get even more complicated when you consider the number of surfaces that each app runs on. There's iOS, there's Android, there's web, and oftentimes there's a desktop app as well. If you do some simple math, multiplying the number of applications that we have messaging in by the number of surfaces that these applications run on, you get to a number. That number is pretty large, but it pales in comparison to the number of challenges that come when running at our scale. Before we dive into some of these challenges, let's take a moment to talk about the timeline of how messaging, specifically in Messenger, has evolved over the years. Messenger started as an acquisition of an app called Beluga. By 2011, it had been relaunched as Facebook Messenger, becoming one of Meta's first standalone apps. Keep in mind that mobile app development was still relatively nascent at this point, with the iPhone having launched just 4 years earlier in 2007. From then on, we continued to add more features and attract new users, hitting 1 billion monthly users by 2016. As a fun fact, one of these features was stickers, and Messenger was the first US app to support sticker sends. While we were really excited by the explosive growth, it started to surface scaling pressures as we continued to amass features. This motivated us to launch a ground-up rewrite of Messenger in 2020, which was 1/4 of the size and twice as fast. In the years since, we've been taking the technology that we built and we've been applying it to the rest of the family of apps. To build our own messaging platform, we needed to understand our customers, the engineers building all of these amazing features over the years. At Meta, we build product incrementally, using A/B testing to build features in small chunks and improve on them iteratively. These A/B tests serve as a feedback loop and inform what we do next. Within this culture, architectural work is valued based on how much value it brings to the end user or to the overall efficiency of the system. Now that we've set the stage a bit, let's talk about the key challenge underpinning the mobile messaging platform. At the end of the day, we're looking at a fundamental trade-off between agility and efficiency. Quick product iteration prioritizes agility, but that same agility leads to a highly divergent code base. On the other hand, efficiency wins prioritize consolidation and code sharing, leading to a highly converged code base with a central core. Each type of code base has its own set of trade-offs. A highly divergent code base leads to higher development costs, as different developers write the same code on the different app surfaces. That setup is typically accompanied by higher runtime costs, as the code tends to get sloppier with all these different cooks in the kitchen. Those high runtime costs snowball into high maintenance costs, as each surface has its own on-call for Android, for iOS, for web, and discrepancies between the surfaces lead to more bugs that need to be fixed. A highly converged data code base requires high ecosystem specialization, as developers now have to write code in a way that supports all the messaging needs of all the different surfaces one time correctly. that typically requires guardrails to be put in place that increase developer friction, slowing product iteration by having a single bottleneck that might be efficient but slows down the developer. So how have we dealt with this trade-off historically? We've found that bigger apps like Facebook, Messenger, and Instagram have a tendency to favor agility because they have more resources. With so many developers, there's a bias towards building custom solutions as we optimize for each surface. For example, even though iOS and Android Messenger share a common server protocol, they had two entirely different syncing strategies. In iOS, they would keep server payloads in memory in order to reduce user-perceived latency because persisting them to disk would take longer. In this case, they were trading off reliability and for performance. In Android, they would do the opposite, trading performance for reliability. As you can imagine, when the time came to increase consistency and remove pull to refresh from Messenger, the two clients had completely different bug profiles. On iOS, we had many bugs related to message loss after restart. On Android, we'd encounter strange UI effects where you could scroll down your inbox and suddenly get kicked back to the top as the client dealt with a complex update path involving many round trips to disk. On the other hand, smaller apps are more scrappy. Around 2015, Meta launched Workplace Chat, a distinct application that is part of our business offerings and features some of Messenger's feature set. The Workplace Chat engineers wound up relinking the entire Messenger application, just with a different icon and a few different dependencies. This lasted until 2021, so for many years they shipped code for many features that they never needed and never used. The takeaway here is that neither extreme is really correct, and we have to work hard to find a balance between the two. In order to achieve this balance, we knew that the solution we build would need to enable code sharing, while still maintaining the developer flexibility that we prize here at Meta. With this in mind, our first step was to determine the type of platform model we wanted to follow. Typically, platforms come in two forms, a service model or an ecosystem model. In a service model like WebRTC, the application links your library and calls functions that your library exposes. In an ecosystem model, it's a bit different. An example of this is Unity. The application not only links your library, but your library defines the way that code in the application is written. So, naturally, we had to ask ourselves the question, is messaging better expressed as a standalone service or as an ecosystem? Many developers expect messaging to be a service. After all, it has pretty clear APIs that, in theory, should make it easy for the UI to build on top of. Take Facebook Stories as an example. As a developer implementing the story reply feature, you would reasonably expect the messaging platform to provide you with a send message API and a send reaction API to invoke accordingly based off of the user interaction. Unfortunately, the example of Facebook Stories is not representative of typical messaging flows, which lean heavily on the notion of side effects. One such side effect is that when you enter a chat, the person on the other end should see a scene head indicating that you have read their messages. Another common side effect is the one that happens when you send a message. In this illustration, you can see that sending a message causes a chat bump, where the chat gets elevated from maybe somewhere in your inbox to the top of it, and gets marked as unread in the process, which is the bolding that you see in the UI here. The complexity of these interactions make developing a quality messaging UI deceptively complex, and giving the application so much responsibility tends to put a strain on the service model. So we determined that in order to correctly encapsulate the notion of side effects, we would need to follow the ecosystem model. And so we created MSys, short for messaging system. MSys is an ecosystem built entirely around SQLite. It is highly relational, with all features being expressed in relational tables like chats, messages, attachments, and so on. You can imagine that there's a complex tree where threads and messages have many tables foreign keying into them. MSys serves as the data layer for messaging, providing a messaging SDK which performs read queries and database mutations under the hood. It's built on a foundation of primitives and data structures, and it has its own infrastructure that leverages a healthy amount of dependency injection from its hosting app. Conceptually, MSys works by expressing the UI as a query against a database. In this example, the inbox is simply a select over the chats table. Similarly, a chat is just a select over the messages table, and the UI uses the sender ID column of the messages table to determine which side to align the messages on. You can imagine that adding a new feature to MSys boils down to adding a new table or a new column to an existing table. In this example, building the Active Now feature, or the green dot that users expect to see when their friends and family are online, it requires creating a new presence table and updating the inbox query to join against this new table. Having a bunch of developers write handwritten SQLite C code is pretty error-prone and complex. In my opinion, it's the opposite of agility. As a result, we created our own DSL called CGCQL. It compiles to C, and we use code gen bridging to Java and Objective-C to power our messaging SDK. With MSys, we also give each app the ability to specify the set of tables and stored procedures that they want to include. Operating as a sort of headless messenger, MSys allows different app surfaces to share components like model generation and syncing logic, but it doesn't enforce that you have to use them. I mentioned earlier that MSys was built for Messenger, but its first test as a platform came when it was integrated into the Facebook app. Messaging has a rich history in the Facebook app. In 2014, we removed messaging entirely from the app, but in the years since, we had different product needs that required us to incrementally bring some of that functionality back. In 2019, we fully reintroduced the inbox experience in Facebook, using code based on GraphQL that was completely disjoint from the Messenger codebase. Having said that, in preparation for our shift to end-to-end encryption, we decided to bring MSys into Facebook as a replacement for the GraphQL solution. Unfortunately, the integration took roughly 2 years, owing to the many scaling challenges that come from taking a platform that we built first for Messenger and trying to apply it more broadly across the family of apps. This time lost was valuable and could have been spent building new features. In the end, the effort did bear fruit, with 25+% reductions in time to interact for inbox and stories when using MSys compared to GraphQL. More recently, we've taken code sharing a step further. Thanks to the Messenger rewrite in 2020, our thread view was modular and small enough to be reused wholesale. This unified the chat views of Messenger and Facebook iOS entirely, and brought many features and interactions from Messenger over to Facebook with almost no engineering cost. The impact on users was also extremely significant, with many finding the experience to be much more engaging. The journey of MSys in Facebook is just one anecdote in a long list as we scale the platform to more apps and surfaces. But as we scale MSys to more clients, we continue to get exposed to new challenges. For instance, we now must tackle the challenge of duplication versus platform cohesion, as dependencies like logging create redundancy in some apps. At the same time, clients with particular needs, like Facebook Lite, push us to increase the granularity of the MSys building blocks so that they can be a bit more selective in what they use and what they don't. Last but not least, differences between our feed-based apps and our inbox-based apps raise interesting questions around the life cycle of MSys. This is because in feed-based apps, messaging is secondary. As a result, initialization of MSys will need to take a back seat to the initialization of, say, the Facebook timeline or the Facebook newsfeed. Similarly, the concept of permanent failures in MSys does not really exist in feed-based apps because a user can still engage with the other parts of the app even if messaging is unavailable. If you contrast that to inbox-based apps, messaging is a primary motivator for user engagement. So startup time and permanent failures are really critical to the experience. Looking at the challenges we've uncovered, we see a lot of opportunity to enhance MSIS even further. The efficiency gains we've seen with MSIS are undeniable, but our challenges suggest that we have more work to do in order to boost agility. To that end, we are exploring new frontiers. We are relaxing the constraint that all the data in MSIS has to be relational. We found that creating a new table or a column for each feature can be cumbersome, and it introduces tech debt if that feature later becomes unused. We're also exploring the introduction of multiple databases in MSIS, allowing us to boost granularity and exercise greater control over what we initialize and when we initialize it. Lastly, we are focusing MSIS more on core messaging flows and investing in better integration at the app layer to help us more easily interoperate with other services that our apps already depend on, like GraphQL. Thank you for watching this talk. For more info, check out the blog post and feel free to reach out with any questions.
Thanks, Akshay. To make it easier for mobile app engineers, they need to see the results of their code changes quickly. By late 2020, Instagram's iOS app had become more complicated, and it took a long time for engineers to see their changes in action. Now let's hear from Meta software engineer Nate Stedman. He will talk about the hard work Instagram's team did over the last 2 years. Nate will explain how they reorganized their code and made the process of building the app faster. The great news is that builds now finish in just 1/6 of the time they used to take. Over to you, Nate.
Hi, I'm Nate. I'm a software engineer at Instagram. I work on our client infrastructure team. I'm here to talk about how we significantly improved the build speed for our iOS app. So this starts out in 2020. It was a big year. Instagram turned 10 years old. So 10 years ago, Instagram started out with Feed, but over time, it has grown to include more features. It's features like Explore, Stories, Direct, and most recently, Reels. 10 years of product growth also meant 10 years of code-base growth. So product engineers love looking at graphs like this. The line's going up, people are using the app. Infra engineers, on the other hand, view graphs like this a little differently, especially when we add some labels to the y-axis. So this kind of graph is what we saw after 10 years of Instagram's iOS code-base growing. We had more classes, we had more libraries, we had more lines of code, those libraries had more dependencies between each other, and our build times had gone way up. When I first joined Instagram in 2017, I remember being able to build and install the app in about 20 seconds. But by 2020, this time had increased to about 2 minutes. We interviewed senior product engineers for qualitative feedback about how this affected their work. While we knew that the numbers were large, product engineers told us it was actually much worse than the numbers showed. The times were so slow that they would lose their focus and lose even more time to distractions. So here's what I'm going to cover today. First, I'll talk about the distinction between initial and incremental builds. I'll then talk about how we improved our incremental link time by splitting and parallelizing our product code, and finally how we scaled this to product teams across Instagram. So initial builds are the first build an engineer does after pulling new changes. It's usually done once or twice per day. Now, these builds need to download a lot of artifacts from our build cache, and that takes a lot of time. It depends on their engineer's internet connection as well. Incremental builds happen when an engineer makes a change and then wants to see it on screen. And it's very disruptive, like we saw earlier, for that to take minutes. And based on the feedback that we received, we knew that this was what we needed to focus on. Initial builds aren't as much as a problem. While they do take a lot longer, engineers do know it will be slow, and it only happens once or twice per day. So they can check their email, they can grab coffee, they can review other engineers' code while an initial build is running. There are what we call workflow workarounds here. So we knew we needed to improve incremental build time. Now we need to know, why is it so slow? One idea is that it was due to the amount of code we needed to compile. So the codebase had grown so much, there were so many more files. But it wasn't compilation. At the time, our codebase was still mostly Objective-C. Objective-C has a lot of disadvantages compared to Apple's modern Swift language, but compile times are not one of them. Objective-C compiles very quickly, and it's very parallelizable due to the use of header files for imports. On an incremental build, we're also only compiling a few files, sometimes only just one. When we looked at a trace of the time spent in an incremental build, we found that most of the time was spent linking and bundling. So linking is the step that combines all of the compiled files into an executable binary that you can run on an iPhone. And bundling is when that binary is combined with resources, so that's things like images, string translations, into a full iOS app that we can actually install on an iPhone. This work was done from scratch on every build. So while most incremental builds only compile 1 or 2 files, all of the linking was redone for the entire app. And even when we have to do more work in this compilation phase, we're able to parallelize it because we have so many different source files. That wasn't the case at all for linking. Okay, so we knew we needed to reduce linking time on incremental builds. Now that we'd identified the main problem, linking, how do we fix this? So we have one big binary containing all of the code in the app. Linking can be broken up by creating what are called frameworks. Rather than having a single binary, some of the code is added to a dynamic library that the binary loads when the app starts. In incremental builds, we're then able to skip relinking the framework if none of the source files that go into it have changed. We can take this further and divide it into more frameworks. So Instagram, the binary, would get smaller and faster to link. Okay, but how do we decide what code goes in which framework? The first option is to do it manually. So source files are grouped into libraries. We could then manually assign either individual source files or libraries to frameworks, and this is how it works in traditional iOS development with Xcode. You create a framework target in Xcode, and then you can directly just add source files to it. You set up your dependencies between frameworks in Xcode. This is something any iOS engineer will be familiar with. But we don't use Xcode directly for building the app. We just use it as a development environment, but this would translate fine to our build system that we do use called Buck. However, we decided manually wouldn't work for us. Instagram is just too big to assign the code manually. We have thousands of libraries. We have millions of lines of code. The list of assignments would be huge. Engineers would need to actively decide when they add a new file where that file should go, and it would add overhead to the development process and create opportunities for making mistakes. Our features are also very tangled, so this is just a subset of what our dependency graph looked like when we started this project. Each dot here is a library, and I've color-coded them by the feature. So one feature is direct, one feature is feed, etc. And while libraries do tend to cluster together within a feature, there's many bidirectional dependencies between features. Another option would be to develop an algorithm that we could run on the dependency graph. However, we decided that trying to do it automatically by an algorithm would not work well either. Seemingly small changes could drastically alter the entire dependency graph. It would be easy for an engineer to accidentally break something, and it would be really confusing for them to debug. This isn't the kind of thing a product engineer runs into on a daily basis. We also didn't think an algorithm would even work that well. Since everything is tangled, how do we break that up automatically? We can't have dependency cycles between frameworks. It just doesn't work that way. And we really want to get to a point where we can have parallelism. And that might not actually be feasible with this existing tangled dependency graph. So we decided to use the structure of our code base. At Meta, we use a single monorepo for all of our mobile code, and it's called fbsource. In the root, there's a folder called explat, and that's for code that we share with Android apps. There's then a folder called fbobc, which is where all of our iOS code lives. That also includes Swift. It's just a very old name. Within fbobc, we have a folder called libraries, and that's for code we share with other iOS apps, like the Facebook app. And then finally, we have a folder just for Instagram. So taking this a.framework and b.framework idea, we turn that into frameworks for the explat and fbobc directories. Most of the Instagram code stayed in the main binary. Code added to explat or fbobc libraries was automatically added to the appropriate framework. We then added dependency rules to prevent dependencies on fbobc from explat and on Instagram from fbobc. So if a violation was introduced, the build would instantly fail locally. This gave engineers immediate feedback when their change would not be allowed. So time-wise, that splits our linking up about like this. Explat takes a really long time to link because it contains a lot of complicated C++ infra code. We can't use Objective-C really in explat because we're sharing the code with Android apps. Fortunately, this is the directory that Instagram product engineers touch the least. So on most builds, we're able to skip that, and often the first 2 parts, and we're only doing about 30 seconds of linking. So checking in with where we started, that looks pretty good for 4 years of code growth. Hey, it's only 10 seconds slower. Except that's just the link time. The overall numbers still look like this at the end of 2021, so we still need to do a lot better. Okay, now we need to bring down the Instagram binary more. What is in here? So what's left is a lot of product code. We have all these different features that I talked about earlier. How would we decide what order this should be linked in? Does stories come before reels? Does reels come before feed? The only way that really made sense is for these to be linked in parallel. It gets rid of this which first question, and it will also just have the best performance. We can use multiple cores to link at the same time. So these frameworks would fit in here after all of the other frameworks we already have, but before the main binary. The binary just always has to come last. That's the way it works. But okay, let's go back to this. Our features are very entangled. We also didn't really have any structured organization for our product code. Some teams created folders, others put hundreds of libraries in the root here. There was no guidance or strict rules on this. The folders didn't do anything, so you could just put code wherever. We started first by finding our own Instagram-specific infrastructure libraries, and we moved those into a folder that we called core. To do this, we mostly just used an eyeball test. The library names are pretty obvious. If it's IG Analytics, IG Networking, it's pretty obvious this is generic infrastructure and not something just for one product. So we added build time dependency rules again for the new core directory. Instagram code outside of core could depend on code inside core, but not vice versa. If a dependency on a non-core Instagram library was added outside of core, the build would immediately fail. This test was another way that we could move libraries into core. If a library didn't have any remaining non-core dependencies, it was a candidate to move. But we'd still need to look at it manually just to see that it was really cross-feature code, not product code that happened to not have any dependencies. So we're also able to move this code into a new framework, the core framework. A common problem that we found when doing this was something that we named dependency magnets. So this is core app infrastructure like URL routing or push notification handling that had grown to depend on the entire app. If a feature needed to integrate, it was imported directly and then it was called. This code was really not well structured, so typically there was a very long if-else chain checking a string for each product case that was handled. These files tend to start out simple and it doesn't look too bad, but then as the product grows in complexity, the files also grow in complexity. Eventually, it just depends on the whole app. We needed to get rid of these. So we replaced them with an internal dependency injection framework that we have that allows us to inject features at build time without explicit code for each one at the call site. This inverts the dependencies between infrastructure and product. Now the product code depends on a shared interface for infrastructure. These injected features then get tagged with the correct string key for their feature. So for URL handling, it would be part of the URL. And the infra can then call out to them without knowing the exact code that it's calling. So removing core made Instagram a little bit smaller, but we have a lot more product code than infrastructure code. Next, we needed to pull out one of the products. When we pull the first product out, it would look like this. Each product is a small part of the whole. So we also need to do this incrementally. Remember, our dependency graph looks like this. There's no way that we can refactor all of this code at once. But we had to start somewhere, so we broke some dependencies, pulled out a small amount of code. Like with core, we also set up the dependency rules. So product code could depend on product code from the same product, could also depend on core, but it can't depend on code outside of the same product. The rest of Instagram could still depend on the product's code because it comes afterwards in the linking step. Then we pulled another small amount of disconnected code out, and for the first time we had linking in parallel. It all worked, the app built, it ran. So most of the code is still in what I'll call the remainder. This code was still getting linked every time, and while we proved the theory, it's not actually that much faster because we haven't moved that much code. In the future, once we moved all the products, then it would look something like this. Everything's in parallel, linking is very fast, we use every core on the machine. So we did the small initial work on our own, but this wouldn't scale to the entire code base, we're just a small team. There's too much code to refactor, we need to evolve the product teams that own this code. Product teams, of course, mostly work on the product. They have time for refactoring improvements, but it's not infinite. And they have plenty of refactoring ideas to go around in their own code base. If they do this work, what would they get in return? Ideally, everyone just does it at the same time. And so everyone gets this, really fast builds. But unfortunately, it's just really hard to get every product team in a large organization to commit to doing a single project all at the same time. In practice, the initial volunteers get to join the frameworks before the Instagram remainder, and unfortunately, that's not actually faster for them. It's a little bit faster for everyone else because other teams can now skip relinking their code that has moved out, but the team that did the work is still linking their code, and then they're linking the remainder on every build. So not much uptake on this. Not a great reward. We needed a different approach. All right, back to the remainder. Well, what if we go in the other direction? If we put the product code after the remainder, then teams whose code lived there would skip linking the remainder. The problem was that the remainder is the Instagram binary, and frameworks just need to come before the main binary. That's just how it works. But this was easy to solve. We could just put the remainder in another framework, and then we just have a tiny binary at the end. So while we're still linking this binary on every build, because it's so small, it links very quickly. We barely even notice it. So we still have this problem, but now we're attacking it from a different direction. Before, we were breaking dependencies on the remainder from a product. Now we need to break dependencies from the remainder on a product. This sets up the right incentive for product teams. If they did the work, they would be immediately rewarded with faster build times. The more code that they moved into their product framework, the higher the chance that one of their builds would be significantly faster with the remainder removed. The idea was still unproven though. We had a strong belief it would work, and that the improvement for the first product team to do this would be huge, but we didn't have any specific example to point to yet. So we convinced the Instagram Direct team that we should have what we called a modularity sprint. And we set up with them for a week and broke dependencies, the end result being Direct framework. We moved everything at once to get an idea of the improvement, and it worked. 2 weeks later, the Direct engineers were linking only the Direct framework 45% of the time. We called these fast link builds as opposed to slow link, and we saw that they were 50% faster. So this got us to 19 seconds if it was a fast link build. So it worked. We got back to the 2017 numbers. What next? Well, we just needed more fast link builds, and so it turns out that infrastructure engineers can like a graph like this. Next, we need to scale this up to more teams. And now that we have the Direct example with actual numbers, we had something to point product teams at, 50% faster. So we set up dashboards that teams could use interactively to explore their build speeds and see improvements. We could also detect libraries that were eligible, and we could even automatically change the code base. But we needed to be careful here because we don't want to move things that are eligible but don't make sense, right? It's the zero dependency library case again. We also added suggestions and warnings to our continuous integration system. So when engineers added a library or changed dependencies and something could be moved into a product folder, we would suggest that. So where are we today? We now have 31 products. Every one of them can link in parallel. This situation has improved a lot. Here's an updated dependency graph using only a few of the products. With all 31, it basically becomes unreadable. Each large product has internal dependencies, but there are zero cross-product dependencies. There are also some satellite libraries that you can see floating around on the periphery. These are very simple libraries that integrate only with the build time dependency injection framework, so no code depends on them directly. This is really helpful for build speeds. The linking layout now looks like this. We still have the remainder, it's still there, but it has become much smaller. And this actually, now that we've gotten this far, helps all teams, even those that haven't moved their code. So if teams are working in the remainder and they don't get a fast link build, they're still benefiting from the parallel linking of code that used to be in the remainder. With these 31 products, we're now up to 35% fast link builds. They're not as fast in relative terms as they used to be, but they're still just as fast. Non-fast builds have also become faster because we're shrinking the remainder, and eventually we expect these builds to entirely disappear. These build speed reductions have significantly improved iOS product engineers' experience at Instagram. To learn more details, check out my blog post on the @Scale site. Thanks for listening.
Thank you, Nate. Earlier this year, Instagram took on a big project. They transitioned an extensive code base, more than 50% of its lines of code from Java to predominantly Kotlin. Today, we're lucky to have Meta software engineer Lisa Watkins explain how they did this. Lisa will not only unravel the technical and cultural challenges, associated with migrating a complex code base from one language to another, but also illustrate how this transformative move paves the way for the future of UI development through the adoption of Jetpack Compose. Now let's hear from Lisa.
Hey everyone, my name is Lisa and I'm here to talk to you today about our Kotlin journey at Instagram. So before I share more, just a little background about me. I've been with Instagram or Meta for about 2.5 years. I joined Instagram as an Android engineer on our mobile infrastructure team. The team has gone through several rebrandings and iterations, but the mission has always been the same. Today we're called the Instagram Developer Craft Team, and our mission is to empower Instagram product teams to ship code fast and reliably. So our team works on anything that can benefit the developer experience, and this ranges from just core infrastructure APIs to even developer tooling. Kotlin was first put on our radar in 2018, and that might seem a little late to the game, especially for those of you who have been writing Android code for a while. But migrating a code base of our size from Java to Kotlin was pretty challenging simply due to the scale of our code base. So the Instagram Android code base is about 8 million lines of code, and we have around 250 Android engineers. Instagram exists in the same repository as many other apps in the Meta family, and these apps include iOS apps, server apps, and other Android apps. To give you an idea of that scale, in our monorepo, we have over 100 Android apps alone. This Android code accounts for 33 million lines of code within the monorepo, and we have about 1,500 Android engineers across Meta. So a large infrastructure change like migrating Instagram to Kotlin involves a lot of coordination with teams outside of Instagram across Meta. And just because of the scale of our monorepo, we had a lot of challenges on this path to Kotlin that I'll get more into later. So now that I've sort of set the tone for the scale of Android development at Meta, let's talk some more about just our typical Android workflow. So we use Buck as our build tool. Many apps out there use Gradle. Today, they're a lot more similar than they used to be, but historically, we built Buck in-house at Meta to combat the build speed problem with that much code at the company. So as you can imagine, in a code base of our size, build speeds becomes increasingly important to developer productivity. The last thing you want to do is hit build to build and install the app to test a feature, and then you have to wait 20 to 25 minutes just to be able to see the app on your device. Android Studio is our IDE. We have built a lot of custom plugins and tooling on top of Android Studio, so the experience is a little special at Meta. And as I described earlier, we exist in a monorepo with most other Android apps at the company. Now, historically, the language of choice for Android development was Java, but I'm here to talk to you today about how that became Kotlin. So to back up, a little bit of what we're talking about today. So first, we'll talk about why Instagram chose to invest in Kotlin, and then we'll talk about the path to adoption. We'll wrap up with a little bit more about the future of our Kotlin investment at Meta and what the future holds. So as we discussed earlier, making the decision to shift from Java to Kotlin was a pretty huge undertaking, and that's mostly because of the size of just Android development at the company. So what makes Kotlin worth the investment? Kotlin was equally an app reliability play and a developer experience play. Null pointer exceptions are the #1 cause of user crashes at Instagram. Java is not a null-safe language. Kotlin is a null-safe language, so it forces you to handle nullability thoughtfully. Less user crashes obviously means a better experience for our users, but also less developer time spent on null safety bugs and sevs. Furthermore, Kotlin has a lot of syntactic sugar that makes writing code intuitive and concise. Kotlin has a better functional programming style support and language features like smart casts, coroutines, extension functions, just to name a few, all of which make code simpler and more robust. JetBrains also benchmarks that the same program written in Java versus Kotlin The Kotlin version will have about 40% fewer lines of code. Less code means easier diff reviews, less to maintain over time, and less legacy code that just becomes tribal knowledge in the future. App reliability and developer experience are very compelling reasons to invest in Kotlin, but a third reason is pretty simple. Our developers just wanted it. So these are a couple quotes from Instagram product engineers using Kotlin, and they attest to how much people love writing Kotlin code and how people feel empowered to write code quicker and more reliably. So we made a big bet at Instagram that Kotlin was the future of Android development across the industry. And this meant that perhaps in the future, modern development would maybe be blocked on using Kotlin. This was a little bit of a bet, but it's been pretty true. Declarative UI, for example, is unblocked by adopting Kotlin. Many of you might be familiar with declarative UI, frameworks like Jetpack Compose or Swift UI. These are gaining popularity across the mobile development industry. Declarative UI just simply allows you to declaratively write UI elements in only Kotlin versus the legacy APIs that involved writing both Java code and XML. Instagram has increasingly been looking at Jetpack Compose as the future for our UI development, and Compose is written for Kotlin development. Compose is another developer productivity play. So this new style of UI programming also results in fewer lines of code, and the syntax is a lot clearer, which means that UI code is easier to maintain and write over time. As Kotlin gained popularity in the industry and frameworks like Compose started popping up, it became more and more clear that modern Android APIs are built for Kotlin. And it almost became indisputable that not migrating to Kotlin almost put Instagram at Meta at risk long term. So once we found alignment in why we were investing in Kotlin, we got to work on Kotlin adoption throughout the Instagram codebase. So our journey really begins in 2019, and this is the point at which we first started investing in addressing infrastructure blockers that were blocking simply compiling Kotlin code within the monorepo. So this work involved working with our Buck team to ship Kotlin support for Buck, and we also partnered with a few select product teams just to sort of pilot what does it feel like to write Kotlin code at Instagram. By the end of 2019, we had about 7,000 lines of Kotlin code in the Instagram codebase. From there, we had the confidence to widen the net of people writing Kotlin code at the company. And in 2020, we focused mainly on, instead of just enablement, how could we improve the developer experience of Kotlin so that it was at parity with the experience of writing Java code. So a lot of our focus at this time was in our continuous integration pipelines, shipping lint support, basically just closing the gap between developer experience writing Java versus Kotlin. In 2021, we announced that Kotlin was an open adoption. So this meant that any team could freely write Kotlin code at Instagram, and all of our infrastructure improvements at this time really focused around performance. So for example, a really big project at the beginning of 2021 was working with our Redux team to improve app size for production builds using Kotlin. Many of you might be familiar with Redux. It's just an Android bytecode optimizer to make app size smaller for production builds. It kind of obfuscates like method names, things like that, to just make the binary smaller. And we didn't want any difference between Java and Kotlin at this time. So by the end of 2021, we announced that Instagram was Kotlin first. Now this means that we expected all new code to be written in Kotlin. So these two graphs kind of paint the picture of how Kotlin adoption progressed at the company. Both graphs start at January of 2021 and end at September of 2023. We've got percent lines of code on the left, and we've got the number of Buck targets with Kotlin code on the right. So today we're at 63% lines of code in Kotlin at Instagram, which is really exciting. And this is basically tripled from January of 2021, which was around 20%. Earlier in 2023, we surpassed the really exciting milestone of half the code base being written in Kotlin, so 50% lines of code, which was very exciting. Once we enabled Kotlin adoption, growth was pretty healthy and organic. Like I said, people love writing Kotlin code. This was not, however, without a pretty large speed bump. So as Kotlin grew in our code base, our build speeds regressed dramatically. So in 2022, this was around the time we hit 30 to 40% lines of code in Kotlin. We were collecting signal that our Android build speeds had more than doubled, so they regressed by over 100%. As I sort of mentioned earlier, with the code base of our scale, build speeds are always top of mind. It's a major hit to developer productivity if you have to sit there and wait for a build. So this is bad. But why was this happening? What makes Kotlin so much more expensive than Java? So for one, the Java compiler is just more mature, and therefore it's just faster than the Kotlin compiler. People have been iterating on it, making optimizations on it for years. And so from a throughput speed perspective, Java is just going to be faster for now. Buck support for Java is also a lot more mature than support for Kotlin. So remember, we built Buck in-house at Meta some time ago, and the team has been iterating on Buck feature sets with a Java in mind. And Kotlin was something, completely new that was just put on the map in 2019. Additionally, earlier we talked about all of the reasons we love Kotlin, all of that syntactic sugar like extension functions, data classes. All of that stuff is really nice from a developer experience standpoint, but it comes at a cost when it comes to the compiler. The compiler is going to be a little bit slower when handling some of those language features, which is more prevalent in Kotlin versus Java. So we've got 3 graphs here that are sort of explaining the cost of building Kotlin code. On the y-axis for each graph, we've got time spent compiling. And on the x-axis for each graph, we've just got percent lines of code. Now, let me draw your attention to the leftmost graph, our most simple graph. This is just showing you that the more lines of code of Kotlin you have, the slower your builds. Easy enough. So the graphs in the middle and on the right take it a step further by taking a look at the critical path. For those of you unfamiliar with build systems or compilers, basically a critical path is just the longest path in your build graph that the compiler has to compile. And we've got this legend here with a few different critical path lengths. In yellow, we've got the shortest length, which is 1, and the teal line, we've got the longest length, which is about 145. And then the other colors are just, some options in between. So the graph in the middle, we have incremental builds where the ABI has changed. ABI just stands for Application Binary Interface. I'm going to explain that a little bit more on the next slide. But you can kind of think of the middle graph as showing us that the compiler needs to recompile code because something has changed, versus the rightmost graph that doesn't need any recompiling. But as you can see, the longer your critical path, the more dramatic this build speed cost becomes when compiling Kotlin code. So cue in Kasabi. So Kasabi is a set of compiler plugins built for Kotlin in-house by Meta. Kasabi generates source-only ABI jars. Let's back up a little bit. We talked about ABI, Application Binary Interfaces. So basically, when you build any sort of JVM program, your output is a jar file. And a jar file is essentially a zip file that represents all of the JVM code and metadata in your application. So with Buck, every Buck target produces a sources jar file. Sources jar files contain all of the code that's in that Buck target. Additionally, Buck will output an ABI jar. And the ABI jar is all of the public-facing code in that target. So you can kind of think of it like the public API of that target. Now, obviously, that's going to be less code than you've got everything in your sources jar, and you've got just your public-facing stuff in your ABI jar. So those ABI jars are smaller, and the compiler can load them into memory faster. So an optimization that build tools make is using ABI jars rather than sources jars when compiling the application. So there's a couple different kinds of ABI jars. We've got source-only ABI, which is what Kasabi generates, that's on the left, and we've got class-only ABI on the right. Class-only ABI, which is what we were working with before Kasabi, the way that we generate this ABI is we compile the whole target, so all of the public stuff, all of the private stuff, and then we go back in a second step and we strip out all of the private stuff. The way you generate source-only is a little bit smarter. It doesn't have to compile the whole target to be produced. It uses some heuristics to make inferences about things that typically you would only know if you compiled the whole target, but it works a little bit smarter, and so you don't have to put it simply. So this means that you have more parallelization and you reduce the number of cache fetches. So let me take your attention to source-only ABI on the left, and you can see that it's a lot shorter than class-only ABI on the right. Now, this is the same build graph. And you can see that there's more options for parallelization if you're just looking at it from like a past perspective on the graph. So this is why Kasabi is like a stepwise improvement for build speeds for Android. So these two graphs describe Kasabi's impact on Kotlin build speeds. So again, we have percent lines of code in Kotlin on the x-axis and time spent compiling on the y-axis. The graph on the left is for all critical paths of 171, and then the graph on the right is a critical path of 137, so it's a bit shorter. The blue line on both graphs has the least amount of source-only ABI and the most amount of class-only ABI. The purple line for both graphs is the greatest amount of source-only ABI. Builds are not deterministic, which is why there's some variability for the different amounts of source-only ABI for both critical path depths. But in general, you can see the purple line generally compiles faster, and that's the line that has the most source-only ABI. So this is basically telling us Kasabi makes Kotlin build speeds faster. In summer of 2022, Instagram was the first Android app at Meta to integrate Kasabi. Now this made sense because Instagram had the most lines of Kotlin code at this time, and so it was just a natural choice to pilot this new source-only ABI generation tool. These two charts show you sort of the adoption story for Kasabi, which we elected to do incrementally just so that the team could address any bugs or issues that came up throughout the integration. So on the left, we have all of the build steps for a target. The orange part is just Kotlin, and then the purple part is Kasabi. So as you can see, in summer of 2022, the amount of Kotlin goes down, the amount of Kasabi integration goes up. And that graph is just zoomed in on the right, where Kotlin is in blue and Kasabi is in green. So by the end of 2022, about 86% of all Kotlin targets had Kasabi enabled. So adoption went smoothly. How did we see this develop in our build speed problem? So this graph has a lot of information, but take your attention to the baby blue area. That area shows you time spent compiling Kotlin code. The other stuff is compiling other sorts of things, other build steps in the process. Just focus on the baby blue part. We've got time on the x-axis and time spent compiling on the y-axis. On the x-axis, we start in H2 of 2022, I believe. And at this time, it took about, on average, 20-something seconds to compile Kotlin code. Over time, as we started integrating Kasabi and source-only ABI into more and more bug targets, that area shrinks. And toward the end of H2 2022, it took about 10.8 seconds to compile Kotlin code on average. So this was about a 55% reduction in time spent compiling Kotlin code and a 38% reduction in time spent compiling Android code overall. So this was a huge success. At this time, we were also increasing Kotlin adoption. So that means that we were combating making the build speed problem worse, and we were also fixing the build speed problem by converting existing modules to Kasabi. So our work with Kotlin at Meta is definitely not done. There's still a lot of investments we need to make. Particularly, null pointer exceptions are still a big issue. Despite the fact that Instagram is over 50% Kotlin by now, we've still got some work to do, and we're doubling down on Kotlin to solve these problems. In 2023, Instagram is moving on from simply Kotlin first to now Kotlin everywhere. And so this means that our focus is not only writing new code in Kotlin, but we're aggressively migrating existing Java code to Kotlin. One of the ways that we're doing this is with the Kotlinator code mod service, which is built in-house at Meta. Now, if you're unfamiliar with a code mod service, I think I might have touched on this with Kasabi. It also used a code mod service for enablement. But this is basically just an automated way to put up pull requests that developers simply have to approve and ship. So we have some code that we wrote that modifies code with a script, publishes a diff, and then you just accept it and ship it, which is pretty cool. So Kotlinator uses the J2K tool, which some of you might be familiar with. This is the tool that JetBrains developed that basically in Android Studio, when you see that little button that says migrate this Java file to Kotlin, that uses the J2K tool. So Meta built on top of this tool with some pre-processing and post-processing steps to build Kotlinator. These pre- and post-processing steps just try to address some nullability concerns because one of the biggest issues we've seen with rapid Kotlin adoption at the company is nullability. We're working with a foundation of Java code that is not null safe, and we're converting that to something that enforces strict nullability. So a lot of issues that have lingered around and we've kind of gotten away with Java rise to the surface once we convert some of that code to Kotlin. The team is investing a lot into making these Kotlin conversions as safe as possible and eliminating our nullability concerns as we continue to migrate. K2 is the new Kotlin compiler from JetBrains, and they've benchmarked about a 55% improvement in compiler throughput speed. Earlier, we talked about source-only ABI and incremental builds. K2 is just simply faster than the previous version of the compiler, which is really exciting. We're one of the first large code bases at Instagram to adopt K2, and we spent 2023 basically migrating all of our Kotlin compiler plugins to K2 APIs. This has been a little bit challenging because those APIs are still experimental. We're kind of, soon to the game here. So things change with each Kotlin version bump, and the team will have to go back and address any breaking changes from updating the Kotlin version. The APIs are also not well documented at this point in time because they're still experimental. So we've been partnering with JetBrains to solve, different bugs that pop up and maybe ideate helpful APIs going forward. And we look forward to continuing this investment through the rest of 2023. As we look to 2024, Kotlin continues to be a major focus for the team, and we're committed to making Instagram Kotlin everywhere. We are really excited to continue the Kotlin journey at Instagram. It's improved the lives of our developers, it's unblocked modern frameworks, and overall has improved app reliability for our users. If you enjoyed today's conversation, be sure to check out my blog post on the AtScale website. Thanks for listening.
Thanks, Lisa. We're going to take a short break now, and when we come back, we'll talk about how we made and released the Threads app for iPhone and Android. After that, we have an exciting live discussion with experts about React Native. And remember, if you have any questions or ideas for future AtScale events or our Meta technical blogs, you can go to our website at atscaleconference.com or scan the QR code on the screen. See you shortly. Welcome back from the break, everyone. The Threads app launch was incredibly successful, gaining 1 million users in just an hour and reaching 100 million users in less than 5 days. We're all amazed and curious about how they did it. How do you plan such a huge launch? What's the timeline like? And how do you handle the challenges that come up? Please welcome Meta software engineer Cameron Roth. He's here to tell us about the fascinating story behind the Threads app launch. Cameron will talk about the strategies, challenges, and key moments that made it such a big success. From the idea to the fast adoption, Cameron will give us insights into how they launched an app on such a massive scale. So without waiting any longer, let's hear from Cameron.
Hi, I'm Cameron. I'm an iOS engineer at Instagram, and today I'm going to talk to you about our journey making Threads for iOS. I'll touch briefly on the inception of Threads, how we went about building it, some of the iOS challenges we faced along the way, and what we were able to accomplish in an unprecedented amount of time for an app of this scale. Late in 2022, planning for the new year, leadership started thinking about taking a swing at enabling more conversational flows within Instagram. We decided we were going to create a standalone app focused on conversations, where creators and people would be able to easily find each other. And we were going to ship it in 6 months. Shipping a finished app to the App Store in 6 months is pretty aggressive. Creating a new brand is incredibly difficult, and with the time constraints, we thought it would give us our best shot to leverage everything Instagram currently does under the hood. Since we were using the existing Instagram codebase, it made sense to try and recruit engineers already familiar with that code. Instagram has a pretty high craft bar, and we wanted to maintain the same sense of familiarity and quality our users have come to love. We knew we couldn't ship an app that fell flat out of the gate. One of the folks tasked with the project had to start talking about it with other people, and calling it text app could only go so far. At the time, people looped in were told it was called Project 92 as a reference to the first SMS message that was sent in 1992. That became the code name and was kept pretty secretive as far as big company standards go. At this point, we'd recruited a team of people with different areas of expertise to try and help cobble this thing together. Now we just needed to build it. I mentioned earlier we decided to build on top of Instagram, and here's what that looked like. IG is deployed on top of Meta's massive server network, which gives us fast and stable distribution worldwide. Having most of that in place already was a critical reason we were able to ship so fast and scale as quickly as we did. The clients already have a ton of code set up to work with and parse these data models, which they then figure out how to render to the user. The natural point to us was to figure out how to use everything that existed except the UI. Even then, we knew we wanted this to look and feel like Instagram, so we tried reusing core existing views like the navigation elements, tab bars, and the action buttons underneath a post. We started by making a new entry point into the Instagram app, like going in the back door instead of the front, and removing a bunch of stuff we didn't need. This is also how the app's binary size kept shrinking after launch. We were working on decoupling, modularizing, and deleting unused code. Here we can see a very early version of the app with the Instagram tab bar, before and after we built any type of reply grouping logic. Tomer's post here was a reply to Tommy. Without the reply grouping, you can kind of see it being strictly chronological. The thread lines at this point were also just hard-coded to always show the loop, and the buttons were just for show, but you could see something. Navigating an old codebase was going about as well as we'd hoped. Generally painless, sometimes getting things for free, sometimes running into obstacles from people who built an app with completely different assumptions, that kind of thing. When you're building something from the ground up, you have first-hand knowledge and intimacy of every use case in the code, and can think about things kind of holistically. When you start working on code that has hundreds or thousands of different call sites, it's a bit harder to be fully confident what you're changing isn't going to break something else. When you face problems like that, you have to either surgically add on code that doesn't affect the other many uses, or find a way to make sure it works everywhere. Some code is pretty well tested, and some, well, not so much. Doing too much surgery adds a lot of technical debt over time, and one of the mindsets we'd adopted with Threads was that we wanted to leave as little a footprint on the Instagram codebase as we could. There's an old proverb that says nothing is as permanent as a temporary solution. We've all seen code supporting thousands or millions of users that started out as a lightning-fast prototype, never meant to see the light of day. Good ideas are contagious though, and demo code has a way of sticking around. We knew that cutting any corners now would cost us a lot of time in the long run. Saving a few minutes or hours today can mean trading off weeks or months of time in the future to correctly diagnose, debug, or build new features or use cases on top of. Since we already had buy-in to go build this thing and didn't need to worry about getting something working in a couple days, we wanted to build it in a way that could be scalable for future engineers finding their way into the Threads codebase. While we had an eye to the future, we were also careful not to over-engineer our code from the beginning. We built only functionality we needed and were careful and pragmatic about how we structured view models or API flows in a way that would hopefully be easy to step into and extend. Our investments into building a stable client infrastructure foundation here ended up being very instrumental in all of the features we've been able to build since launch. In the same vein, a favorite motto of mine comes from the US Navy SEALs. Slow is smooth, smooth is fast. Missteps or having to do something twice is so much costlier than doing something right the first time. Now, what right is might mean a few things depending on what the context of the situation is, but knowing what success looks like can often be the best path forward. Moving fast isn't very valuable if you're being reckless or having to slow down to fix what you've broken. As software engineers, the number one reason we write code is for other software engineers to maintain that code. Code that works and is understandable is infinitely more valuable than code that works and is clever. Instagram is primarily pretty plain Objective-C with some Objective-C++, typically around video handling and logging. The day Threads launched, there was a public article wrongly claiming we wrote the app in React Native. But that was just because they'd seen that the library was still in our code. We hadn't yet had a chance to delete it. Meta has another language we call blocks that we use for universal experiences or where centralizing some business logic can be important, like user authentication, reporting users, or the help center. We create most of our views programmatically, in code, instead of using nibs or storyboards or SwiftUI. Earlier this year, Instagram made a conscious effort to try and write new code using Swift, and we wanted to really advocate that with Threads. Instagram has started dabbling with SwiftUI, and there are a couple small instances in Threads, but it's not very substantial. This initial login screen was SwiftUI. Instagram and Meta overall generally leave specific implementations up to teams who are best equipped to make those kinds of tactical decisions. But there are trade-offs for things like compile time or cross-team dependencies that you need to be mindful of. Two common types of problems with established and large iOS codebases are ideas relating to type safety and nullability. Type safety, introspection, and reflection are ways that we have as software engineers to verify that an object is the type we think it is and safely perform operations on it. Nullability, on the other hand, is expecting an object and not getting one at all. Objective-C has some pretty great language features around working with objects that are nil and otherwise verifying and guarding against improper use cases. But over the years, as a codebase evolves and is worked on by many people or bots, some of these things can start slipping through the cracks if developers aren't careful with proper annotations. Swift solves both of these problems implicitly in how the language is structured. Those problems can still exist, but you have to go out of your way to make them happen. Most of the code we wrote dedicated to Threads was in Swift, but there was still a lot of touch points with older Objective-C code. And if that old code says it's passing an object to Swift and we don't get an object, we crash. On the plus side, we crash, and now we can solve the issue. In Objective-C, depending on what that code did, could just silently fail for days or weeks without notice. I don't want to say Swift is entirely responsible for the soundness of the Threads codebase or its low crash rate, but it definitely made it simpler for us to focus on what the code should do instead of how the code should do it. A lot of apps are just lists of something. Texts, emails, photos, stories, posts. Almost all of the lists in IG are powered by a library we created and open sourced nearly 7 years ago called IG Listkit. I won't go into too much detail here, but at a high level it allows us to pass around ordered collections of data, feed posts, DMs, reels, and allows the business logic for how to display a specific item to be encapsulated elsewhere. The real magic of the library is that it lets us know which items changed and how they changed, if they were inserted, moved, or deleted. After the list is changed, it lets the adapter and view know, and then we can re-render the list so we get to focus on the underlying data. In the IG feed, most of the underlying objects we pass around is a type called IG media. This object knows almost everything about the current state of a post, including things like who the author is, how many likes it has, the comments on it, and so on. When we render what to show to the user, IG media is mapped to a section controller, the pink here, that is treated as a single unit. That unit then has a collection view of smaller cells that each get rendered separately, that together become what we see here and identify as a feed post. The initial designs for Threads worked with this architecture as well. We had clearly delineated rows of content and would be working with the IG media object. The thread line spanned multiple rows in a lot of instances, but we figured we'd just make it work by having that be part of each subcell. Each separate horizontal unit, so here the header with the username and timestamp, and the replies, don't have a thread line, but the text, the image, the likes, and the interaction buttons would all have the thread line built into each separate row. Progress felt like it was moving steadily, and then we hit a couple roadblocks on some key features that we knew would take a lot of engineering effort to overcome. These all kind of happened around the same time, giving multiple work streams making progress at once, but they aren't strictly related, other than being connected to IG media. Those three problems were a redesign trying to optimize our information density, handling reposts, and some improvements to replies. Our initial designs made the app feel pretty empty once we'd gotten to a point where we could use it. We knew we needed to tighten things up and really focus on the text-first intention. In a conversational app, we felt that reposting content was important to the product experience, but there were no reposts in Instagram. In IG, every post is just a standalone post. If you want to repost, you just make the content new and maybe credit the author. If you want to reply to someone, you can kind of fake it by maybe screenshotting their content in your post and tagging them, or replying to a story in a private setting, but there was no actual notion of a reply. When we started tightening the views to rein in the negative space, we ran into the problem of a row being completely horizontally contained. The main problem here being that the profile picture now spanned multiple lines. You can also see that the text row, if only one line of text exists, no longer has a thread line, but needs one for multiple lines. Here's the problem in more clarity. On the left is the post as we want it to look. With only a single line of text, the profile picture spans 2 separate rows, and there is no thread line visible. Keep in mind, as we were building this, we were always keeping the option to ship quickly on the table. We didn't have time to do a full rewrite of our system, so we did what we could to make it work. We tried a handful of options and ended up on this as the solution. Put the profile picture on every cell. With some clever reuse in base cells, we were able to calculate how much of the profile picture should be shown on each row, and if we should offset it. We also ended up using this to support proper threadline end caps to get the nice rounding. Replies and reposts were a new use of IG Media. This object has a decade of implicit assumptions built into and around it, including that it would only ever exist once in a single surface. A post on your main IG feed can't be in 2 spots. When we show a reply to a thread, we want to show the original post to the user for context. So if you're scrolling and you end up with this post by the Backstreet Boys on the left in your feed, and then scroll some more and see this reply from Zuck to the Backstreet Boys, the top post now appears in more than one spot. None of our infrastructure was set up to support this. The same problem happens with reposts. A repost is kind of just the original post being broadcast again in another place by another user. We had to make a lot of fundamental changes to our underlying ordered data to make sure these worked fluidly. Because of the requirement for uniqueness in IG ListKit, we moved towards a container object that could be unique but reference the same underlying IG media object at multiple spots. This is a rough idea of what this data wrapper looks like. A thread is a collection of thread items, and a thread item is some metadata around a base media object. The interactions between posts and replies that we ended up shipping with is actually a lot more complex than it looks on the surface. Some replies are collapsed, some can load inline, and others are only visible on the thread details page. Knowing we needed to be able to ship at a moment's notice, our milestones were tight iterations on what we were using every day. If our window to launch ever felt like it was right, we needed to be able to capitalize quickly. Now let's talk about our onboarding and launch. Anybody who's worked on a product knows that successfully onboarding users is the hardest part. We wanted to streamline that experience and make it really simple for Instagram users to get into threads. We used users' existing IG accounts for logging in as our name reservation system and hooked up some simple imports to pre-populate the information you'd like to bring over. We also made following all the same accounts you follow today easy to do if you wanted to. A couple weeks before we ended up launching, we revisited our onboarding process to make it more straightforward. Here's a before and after of 2 key screens in the sign-up flow. I know I mentioned doing the same thing multiple times isn't the best way to move forward, but adapting and pivoting based on new information and feedback can be just as valuable. To help broadcast to our users that Threads was a thing, we built a few features in Instagram to help fuel early adoption. The ticket here was just a fun Easter egg to try and leave a trail for people that might stumble onto it, and the joiner badge ended up being wildly successful to the point where there was enough demand for us to bring it back. Being iOS engineers, we felt it was important to have native support for sending an iMessage. This didn't work out of the box for us, but we filed a radar after having what we thought was most of the proper tags populated, and were able to work with Apple engineers on figuring out how to get us up and running. When we were ready to go, Zuck made the first official post, and we hid everything we'd been posting before then from the public. We had dozens of folks involved in engaging with thousands of creators to try and start seeding the platform with desirable content before we open more broadly. Just to kind of look back on the journey, our first iOS Threads commit was in late January. We submit the version that would go live to the App Store in late June, exactly 150 days later. In that time, 30% of the Swift code written at Meta was in the Threads codebase. And that crash rate is not a typo. Most of our crashes were from iOS 17 changes that we couldn't easily accommodate. At Meta, we use a build system we created called Buck that handles the building, caching, and distribution of compiled code artifacts to try and minimize the time developers spend building their apps. Proper iOS 17 support came the following week internally, which allowed us to fix most of the crashes that existed for the next app update. By the end of the 5th day, we'd hit 100 million users, which was by far the fastest of any app ever. While a lot of products don't get the benefit of a pre-existing network, it was still a monumental feat and a whirlwind of emotions over the first week. Not having to build infrastructure that could scale to billions of network requests was one of the countless things that helped us get out the door so quickly. That's most of the story of the birth of Threads. Meta likes to say the journey is only 1% done, and the Threads unveiling was truly just the beginning. We wanted to ship a minimum lovable product, something we could try and use to find product market fit, and getting it into the hands of users was the best way for them to validate what we should be building. With such a tight timeline, we had to ruthlessly prioritize what to build every single day. Once we launched, we got the benefit of millions of users telling us what they wanted to use on the platform, which is a great way to know you're on the right track. Since then, we've been able to launch quite a few improvements. When this talk goes live, Threads will be just 4 months old. But that stable base we spent time building has allowed us to keep moving quickly and focus on building features, not worrying too much about the foundation. A couple weeks after launch, we shipped the chronological following feed, post translations, activity page filtering, and the follow all button. That was followed up quickly with integrated sharing with Instagram DMs, a way to view all the posts you've liked, custom alt text for photo and video production and consumption, enhanced voiceover and screen reader support, account follower sorting, and a mention button on profiles. In a move towards Fediverse integration, we added Realme support in Threads profiles. Hearing feedback from the Threads community, we brought reposts to the following feed, and added a consolidated entry point for viewing the reposts from a user on their profile. The same week, we launched a version of Threads on web that you could just log into and use like the mobile apps, not just read content anonymously. We built and shipped search for actual topics, not just users, and are working on increasing the number of languages supported. We added notifications for specific threads so you can follow along with a conversation on a post that interests you. We built out multiple account support, including fast account switching with the same intuitive gestures you find on Instagram. And that's just the features that made the headlines. Every week we've been shipping love and bringing little improvements, stability fixes, efficiency wins, or more delight to dozens of parts of the app that millions of users see every day. From the time I recorded this to when you're watching it now, there'll be a handful of features launched that people will be stoked to see. In the coming weeks and months, we'll launch more exciting things, and I hope we can keep growing together. If you want more details on what I talked about today, make sure to check out the blog post. And if you have ideas or feedback, you can find us on Threads. Thanks for watching.
Thank you, Cameron. What an incredible journey we've been on. Yet the making of Threads for iOS is only half of what it takes to launch a global app. I invite you to join us for continued learning with Meta software engineer Richard Zadorozny as he unveils the other half of the story, making Android. Richard will explain how his team achieved this impressive accomplishment in a short amount of time. They also used a new tool called Jetpack Compose for the first time. Pay attention as he tells us what they learned during this journey. After Richard's talk, stay tuned for a panel on React Native, moderated by Nicola Cordy. Now, Richard, over to you.
Hi, my name is Richard Zadorozny. I'm a software engineer on the Threads team working on our Android app. And I want to talk to you today about making Threads for Android, especially using Jetpack Compose to reach 50 million people. So I'm going to talk about this going through the journey of building it, starting with asking ourselves, what are we building and how fast? To how we built this with Compose, especially some of the things that we learned by building an app of this scale that isn't really covered in the Compose documentation, and then going over some of the post-launch stuff that happened. So the first question was, what are we building and how fast? So you probably know by now that we built the Threads app very quickly, but our first deadline was actually just 1 to 2 months for our initial minimum viable product. So we knew that there was appetite for a new text-based conversation app in the public, and we wanted to have something ready if an opportunity presented itself that we wanted to get something out there. But building a new social network app from scratch in 1 to 2 months is very difficult. So we had to figure out what would be the fastest way that we could get something ready that was high quality. At Instagram, we pride ourselves on having a high quality bar, so we had to figure out how to get that right balance. So we decided that we would build using Instagram as our base. And we realized that we could reuse our servers and our data layer and then try to build threads on top of that. And you can kind of think about a Threads post as an Instagram post, where just the media is optional. And there's a few more details there, but that's a pretty good approximation. So we just had to figure out how could we build our Threads UI and slightly different business logic on top of Instagram. Well, around this time, we had been investigating declarative UI frameworks for Instagram. And Jetpack Compose is the new modern declarative UI framework that's built by Google. By this time, we had started to make some initial tests inside Instagram. We started to lay the foundation of Compose in Instagram and saw how it would work in our systems. But we know that refactoring a large app like Instagram takes a long time. We have a lot of performance cares inside the main Instagram feed. It has to be really fast. And making sure to trying to change the UI framework while maintaining that high performance would be really challenging. So with Threads, we have a new opportunity where maybe this would be an appropriate way to get a lot of expertise in Compose really quickly and sort of catalyze adoption throughout the rest of Instagram. So we had to make a decision, what would be our best option? With views, because Instagram is built with views, we could adapt our existing Instagram UI for Threads. And all of our engineers have prior expertise in views. We also know that views are a complete framework, but it is kind of legacy now. Google has said that all new components would be built in Compose, but not necessarily in views. And with Compose, we didn't know if it would actually do everything we needed to yet, but we knew we could interop with views and fragments if we needed to. And we didn't have a lot of expertise with Compose yet, but we saw that the ramp-up time was actually pretty good and that people really appreciated the nicer developer experience and how it was easier to apply modern practices. So we saw Compose as a risk because it was some unknowns there, but I saw views as a big risk too, because we've seen that trying to refactor and adapt our Instagram UI to something new takes a long time and it's really challenging. So we decided on Compose. So let's talk about how that went. And again, I want to focus on some of the stuff that isn't covered in the Compose documentation, stuff we've discovered by building a big app of this scale. Of course, no matter what, you always start with an empty activity. Nothing's different at Meta about that. But 2 days later, we have something that actually looks pretty close to the final product. We have our threadline decorations on the side there. We have our feed. We have the buttons, the reply text at the bottom. We have the tab bar. And it scrolls. It's looking pretty good. But it is mock data. This is not real data at all. And a lot of those tabs are actually blank. But pretty good progress so far. In another 2 days, we have real data. So the nice thing about building the UI from scratch is we could get something that starts to look good really quickly, which is really motivating when you're trying to build something really fast. But don't be fooled. It's still not ready for 50 million people. You still have to build the rest of the owl, so to speak. There were no images there, the carousels, videos, activity feed, likes list, search. There's so many features that go into building a complete social network app. And so something I want to say is, I talk a lot about Compose in this talk, but a good app is more than just a good UI framework. It's also the people. And I feel very fortunate to work alongside a group of highly talented native Android engineers here at Meta to build this, and without which this wouldn't be possible to build it so quickly. We also took a very principled approach to development. We didn't have an example of what a Compose app would look like at this scale. So we had tried to apply clean code principles as responsibly as possible, avoiding early abstractions and continuously iterating on the architecture and design as we went. Because we kind of were figuring out what we were going to build as we were building it. So we did run into some challenges, and I want to talk about some of the ones that I found most interesting. The first is Compose upgrades. Now, when we started building Threads, we knew that performance wasn't quite where we wanted it to be, but Google was making significant advancements in performance. So we wanted to upgrade Compose as we were building the app. And this wouldn't be so bad, except that at Meta, we have a mono repo where we have Instagram, Facebook, Messenger, the Oculus app. Every app we've ever released is there, including ones we're still working on. So if we try to upgrade Compose, we're actually upgrading it for all of these apps. And these apps may not really be using Compose yet, but Compose depends on Jetpack libraries, which may or may not depend on Kotlin upgrades. And so this upgrade actually becomes a big deal, because if this breaks any one of these apps, you cannot land that change. But We have been making significant progress here, and we've been able to upgrade to the last version of Compose 1.5 just 30 hours after it being released, and then rolled it into the next version of Threads for Android the next week. So it's just a really big undertaking at this company, but it's super important. All right, I'm going to go into a technical detail now. And I could honestly go into this topic for about an hour, but I'm going to go over it at a very high level. And if you find this interesting, I encourage you to check out the blog post that should be going out around the same time with more details about some of the challenges here and some of the fixes that you can do. So the subject is stability and recomposition, and notably how this can affect the performance of your app, especially as it starts to grow. And there are kind of 4 categories that play into this, or ways that stability and recomposition can become a bit of a problem. So let's go into a little bit about each. The first one is unstable types. And if you've looked into performance and stability in Compose, you've probably heard about this already, but it gets into a little bit more detail here. So stability in Compose is the idea that a class or object, inside a class or object, if any data or value inside there changes, Compose can observe that change and make smart decisions about what to recompose. And this is really good for performance. The problem is that you have to opt into this behavior. So by default, if you create a new class, it is considered unstable. When Compose reaches an unstable type, it will no longer make an assumption about what's inside and will favor correctness over performance. It could recompose a lot more of your UI than is really necessary. So an example here, we have a function myComponent, which takes a few argument types. Context, that's not stable or immutable. We have our own custom class, which hasn't been marked as stable or immutable, and we have a list. All of these are actually unstable types. There are some pretty easy fixes here. One is, if your class can be stable or immutable, you should mark it as such. And if you want to learn more, check out the blog post for what those mean. Some classes have immutable alternatives, like immutable list. For anything else, you need to try to figure out how to defer access to those unstable types as much as possible. So in this case, instead of passing context as an argument, you could get it as a composition local. So it's no longer an argument in that function, and so that argument can now be skippable. The next one is composed modifiers. So in our previous example, we updated our function so that all the arguments were now stable or immutable types. However, it's still possible to pass values to prevent that specific function call, and prevent it from being skipped. So in this example, myComponent is given a clickable modifier, which looks pretty innocent enough, but clickable is built with the composed modifier. This means every time you call myComponent, or you get to this myComponent line, you cannot skip that call. And so we have to try to fix that as well. There are a few fixes. One is, if you can move that composed modifier inside the component, now that component can be skipped and you're kind of pushing the problem further downstream, which might be fine for your purposes. So you could pass an onClick lambda instead. That lambda could be considered stable. Another example, if it is one of your own custom modifiers, you could change how it's written. You could use a simple or a regular composable function to build the modifier instead. Or, if you're interested, you could try the new modifier node API that Compose is working on. It's a little bit more advanced, but it could be better for your scenario. Another issue is lambda recreation. This one was a big gotcha for us in our app and hasn't really been talked about, but I think it's really important to be mindful of it. So this still gets back to unstable types. And you might know about the Compose compiler reports that you can enable, which analyze a function and tell you if its arguments are stable or not. But it doesn't tell you what's happening inside your function. And that's still actually very important. So in this example, we have an onClick lambda, and it's calling our view model, but it's okay. We made our view model stable, so that's fine. And it's using a context. We can see just above, we've used the composition local to get that context. So we should be safe, right? Nope. Context is still an unstable type, and we're passing it into this lambda. So a bit about lambda reuse in Compose. Compose will actually try to reuse a Lambda instance across recompositions. So every time your code is being called, it'll try to reuse the same Lambda instance from last time. But if that Lambda is capturing an unstable type, it will not reuse that instance. It will always recreate it. And if your Lambda gets recreated, that myComponent call cannot be skipped. So that's one scenario. But this problem isn't only in unstable types. It could happen in cases that seem fairly innocent. In this next example, we have perform action that's using a row and its ID. Let's say row is an immutable type. There are actually no unstable types here at all. The issue is that even if a row ID may never change, the instance of that row object might change. Say, for example, you create a new copy of that row where isLiked has been flipped from false to true. We have a new row instance. And so because that Lambda captures that row instance, it's a new instance, and so it has to recreate the Lambda. So it prevents skipping again. So these are some things that you have to watch out for. Now, those cases might seem simple enough, but as your app is growing, there could be a much bigger impact from this problem. See here, it's still the same problem. We have a onClick Lambda that's capturing context. But look at the nested calls that are happening here. Let's say we haven't split up our function into smaller functions yet. The impact becomes very widespread. How does context get from there to here? Well, look at all those lambdas. It means that every lambda has to capture context to pass it to the next one. So if that myScaffold line enters recomposition, that whole thing has to be recreated, which is pretty silly because context didn't even change anyways, so really nothing should have happened. So those are some of the examples that we had seen, and that's still kind of a high-level overview. So if that's something you're interested in, please check out the blog post. We go into much more detail over there, or hit me up in threads. All right, the other example was too many arguments. So Compose encourages a very detailed API for each composable function that you add. You try to pass very primitive data or individual lambdas to your component. And this works very well because you know exactly what that component needs and what it needs to give back. However, as you start building your app, these components start to get a bit more detailed. The list of arguments just grows and grows. And for threads, our feed rows have over 30 actions and events that it can trigger. And there's several problems with this. One, it becomes really hard to reuse this function. Imagine having to call this function with 50 arguments in like 5, 10 other places. That's really hard to manage. And then with all those individual lambdas, it becomes really easy to capture those unstable values or have those other recomposition issues. The other issue with lambdas is that you can't call them with named arguments. And if it's just one argument, that might be fine. But if they start to get a bit more complex and have multiple arguments, it's not a really great developer experience. So the fix, fortunately, is pretty simple. And it is to group those data objects and lambdas into groups. The important key is that when you do these groupings, it should be thinking about what myComponent needs exactly from the outside. It should never be what something else wants to give to myComponent. So myComponent is never getting anything else that it doesn't need. And the other nice thing is because the events are put into an interface, you can call those functions with named arguments again, so it is a nicer development experience. I would still just encourage you to not default to this approach. Try to find those functions that are becoming a bit unwieldy, and then see about applying this pattern over there. The other nice thing about interface is that it actually still gives you a lot of flexibility for how you're implementing this in each one of your screens. All right, so that was a lot about challenges, but we did actually have a lot of fun using Compose as well. So I want to talk about some of the ones that I found the most fun. The first one is the threads icon spinner that shows up at the top of our feed. I was really happy that we got to get this into the initial launch. And there were two things about Compose that made this easy and fun to build. The first is anything built in Material or the other examples that Google has are pretty modular. So back before, this pull to refresh behavior was in a swipe refresh layout, which just had all the logic in one big class. But in Compose, there are several components that you can pick and choose what you want. So we could just reuse the Material pull to refresh modifier for our spinner. and this gives us gesture detection and some state. And then we can just put our custom render and layout logic on top of that. The other nice thing was with Compose's coroutine-based animation API, it was really easy to build this sequential animation for the spinner. So I can kind of show you a little bit about what that kind of looks like or how you can think about it. You can kind of do this or imagine this with a launched effect, which happens whenever you start refreshing the feed. It's just a simple loop. While you're refreshing, animate to the end, animate back to the beginning, and keep going until the refresh is done. And then once that loop is finished, you can just animate, fill the rest of the wave from whichever side you ended up on. And I just find this really easy to read and follow compared to what we might have done before, which was the listener approach where you're just kind of jumping between the functions, but it's just harder to find what the sequence actually is. So that was really nice. Another example is shared element transitions. Now, Compose doesn't have an API for this yet, but we found it pretty easy to build in a way that makes it really easy to reuse across all of our screens. So an example is when you tap on a picture in Feed, it'll zoom in to the full screen viewer, and you can fling it to dismiss. These are two different screens in our Jetpack navigation-based navigation system, but it's really easy to do with how we have it set up in Compose. And I really like this other example too that probably not a lot of people see, which is the picture jumping between two screens that are moving if you're adding some alt text, some accessibility text to your pictures. Another fun one was the UI tuner. And this one's more of a developer feature than something that we publicly show, but maybe this audience finds this interesting. I think what was really neat is how easy it is to integrate a system like this into your app. So Compose does have a live edit feature where you can change code in your app and see it reflect immediately in your app. But what about those times when you're not at a keyboard and maybe you're giving your phone to a designer and you want them to check how it feels or give some suggestions on specific animation values? With our UI tuner, this becomes really easy and really easy to put anywhere in the app that you want it. So for this example, we have a shared element transition when you zoom into a profile picture, but we just have to change the code to call tunable spring spec instead. And then just the presence of this function call in composition will make this field show up in the UI tuner where you can tweak the properties and have some fun with how the thing shows up. All right, so that's some challenges and some fun stuff. Let's talk about the launch. So it's probably not too big of a surprise, but it went well. We launched in 5 months since we started coding the project, and we quickly reached 50 million installs on Android. So that 100 million installs that we got was pretty evenly split between Android and iOS. And I was really happy that our quality was on par with the iOS app, and we had the same feature set. And there were some growth features that we really enjoyed too. One of them we call the golden ticket, and Cameron talked about this a little bit. We had the same thing on Android. This isn't built with Compose, just standard views and canvas drawing. I thought it was really neat that the team was able to build this with a few gradients, shaders, and a bit of love. And also this Threads joiner number in Instagram turned out to be so popular that after a while we took it out, but we had to put it back in because it was just so popular. And in terms of interesting launch bugs, this one was one of my favorites. This only happened on Android 9 devices that had enabled dark mode, and it is gnarly. So when I saw this, I thought for sure it would be a Compose rendering bug, like a backwards compatibility thing. But when I reached out to the Android team, they recommended to look into underdrawing, and sure enough, that was the actual issue. So it wasn't a Compose bug, it was a different Android view kind of system bug where the window background wasn't being set properly on these devices. So fortunately, easy fix, but it's a beautiful bug. All right, so going forward, we are very happy with how Compose worked for building the Threads app. And so we're going to continue doing that. And we're also excited to pursue adoption in the rest of the main Instagram app and throughout Meta. For Threads itself, we're going to continue iterating on the app to try to deliver the best value that you're looking for in a text-based conversation app. Since we launched, we added edit, content search, and we have a bunch of other stuff that we hope you like. So that's how we made Threads for Android, and I hope to see you there. Thank you.
Hi, everyone. Thank you very much for joining us in this panel about React Native at scale. My name is Nicola Corti. I'm an Android engineer working at Meta on the React Native core team, and I'm more than excited to welcome you all with all of our panelists here on stage live at the Mobile at Scale conference. Before we begin, I actually would like to understand from the viewers of the live stream, what is your experience like? Do you know React Native? Do you know what it is? So we do have like a poll that will pop up just above the chat window, and make sure you complete it. And complete it, close it, and like this will help us just to get a little bit of an understanding of if you know React Native, if you use React Native, and so on. And make sure you close it because you will need the chat, because this panel is going to be interactive. So we do have some warm-up questions, but we want you, folks from the audience, to type your questions, ask all of your doubts to all those amazing panelists. So I already introduced myself, and now I want to hand over to the folks here that are joining me on stage to tell us a little bit about what do they do, what's their role, and most importantly, we will also hear now during the introduction, how is React Native used within their organization. We do have a lot of industry leaders out here, so I'm happy to hand it over to Kevin from Meta to start.
Hello, everyone. I'm Kevin. I'm an engineering manager at Meta, working on the React org. My focus has been the React Native architecture. So if you heard the term new architecture, yeah, my team worked on that since a few years ago. For Meta, our org focuses on building core foundation of React, React Native, and Relay, all the three. And we aim the internal developers, all the React developers in the company, and also for external community. So we enable developers internally to build in different platforms, different apps. So we have the main Facebook app, a bunch of other mobile apps in the company, desktop apps, and also VR apps. So that's a bit about me.
Awesome, Kevin. Thank you very much. Up next, we have Caliph from Microsoft.
Yes, hi everyone. So I'm Caliph. I'm an engineering manager at Microsoft, more specifically in the Office division. And so what we do with React Native is we own and maintain the React Native for desktop platforms, specifically Windows and Mac OS, and some open source tooling that help people build React Native experiences. And internally, we use React Native to light up, like several experiences across our mobile and desktop platforms. We have two types of applications, some that are built from the ground up using React Native, which we usually call greenfield apps. And then we have existing native application where we embed views that we use to light up like very specific scenarios. And this is usually called brownfield applications. But today it's used across, Office, Teams, Xbox, Outlook, Power Apps, even the Windows operating system, and a lot of other applications that we have internally. So yeah, that's a little bit about me.
Awesome. Thank you very much, Caliph. Up next, we have Mustafa from Shopify.
Hi, everyone. Mustafa here. I'm a director of engineering at Shopify. I've been doing mobile for almost 15 years now, and I currently lead the team building the main Shopify app and also responsible for application security for all our mobile apps. At Shopify, we went all in on React Native in 2020, and we've migrated all of our apps. So the main Shopify app, point of sale, inbox, balance, and shop have all been migrated to React Native. And we used a combination of greenfield and brownfield approaches to do that. And it's now the default way of building mobile apps at Shopify.
Awesome. And finally, we do have Alfonso from Coinbase.
Hi, everyone. My name is Alfonso. I'm a software engineer at Coinbase. I'm part of the DevX team. I focus on providing internal solutions to facilitate building, testing, releasing React Native mobile apps. At Coinbase, our three main apps, the Coinbase app, Wallet, Prime, use React Native, and React Native is the paved road for all of our apps.
Awesome. So, folks, we got the results from the poll. We got like a significant amount of people that are new to React Native, and then someone that is familiar with it. Let's say 70% it's new. So I want to stress how important it is that now you use the chat to ask questions to our panelists about how React Native is used at scale. Like you have this unique opportunity to ask companies that are using React Native on products that are used by millions or billions of users. So don't miss this opportunity. We're going to warm up the stage with some questions, but please make sure you ask your own so we can make it a little bit more interactive. So as I said, let's warm up the stage with the first question, which is, okay, folks, so you all are using React Native in your products, and I'm sure that at some point someone was sitting down in a meeting and was deciding, okay, we want to invest on cross-platform. Like cross-platform is the way forward. There are multiple solutions for cross-platform. React Native is not the only one. There are others like known solutions out there in the market. Now, I want to ask you, what was the key factor that resulted in your organization picking React Native? And Mustafa, like from Shopify, I know all of your mobile apps are basically in React Native. Do you have something to share about it?
Yeah, sure. For us, the biggest reason for looking into this area was the difficulty in maintaining feature parity. At our scale, like we had native teams building Android and iOS versions of the same app, and just keeping them in sync was taking a lot of time and effort. So we started looking at cross-platform solutions, and React Native was one of them. We picked React Native for a bunch of different reasons. The main one was the maturity of the framework and the ecosystem, and also the familiarity with the language and tooling. We have a very deep expertise in web tooling, so it was a logical extension of that. So that made us choose React Native.
Got it. I want to ask like the same question also to Caliph, because in your introduction you mentioned that React Native is also used in Windows, like in the operating system, and like let's stress how, like, you know, when people think about React Native, they always think about like Android and iOS, but actually it allows to reach a variety of different platforms. So how comes that Microsoft picked React Native?
Yeah, so some of the reasons are similar to what Mustafa just said. Like when we were evaluating cross-platform solutions, we saw that React Native was a very mature platform. Of course, like really early on, the desktop implementations were not there, so we added it because we ship a lot of desktop platforms. But the maturity was really important. We had a lot of web developers who wanted to port experiences over to native platforms, and they already had experience with JavaScript. They understood the tooling, so it was much easier for them to build these applications using React Native than going native. And then the other aspect that there was is that, especially in the case of brownfield applications, we wanted to use modern UI frameworks, but at the same time, we need the UI to look exactly the same within those older applications. And the ability that React Native provides us to embed our own rendering framework was extremely important to us. That's what allowed us, for example, when you were mentioning the Windows operating system, Nicola, that's what allowed us to build some of the experiences in the newer versions of Windows using React Native. But when people actually look at it, there's no way for them to tell that this is actually not using native code directly. And then another reason was just the performance characteristics. There are places where we have applications that need to, that we have experiences that need to launch very quickly. And there's a lot of ways where React Native actually allows us to hit those performance requirements that we had.
Awesome. Thank you very much for sharing your insight, Caliph. I want to touch on like one of the fundamental principles of React Native, which you folks can see if you head over to reactnative.dev. The problem is, like, the motto is learn once, write anywhere. No, like whenever we hear like CTOs or like technical leader talking about let's go cross-platform because I'm gonna write it up only once, no, and like save half of the time. Well, you folks are like real example if that promise holds true or not. So now I would like to ask Kevin, give us a little bit of perspective from Meta on how React Native effectively has impacted the productivity of our engineers.
Yeah, this is very interesting topic because React is about portability of expertise as well. And a lot of developers started at Meta. Maybe they're like a UI engineer or a web developer or iOS or Android. I mean, I am an iOS engineer at start, and learning learning React once means that you can apply this when building multiple products. And I think it's about features in different apps too. So we do focus on building the building blocks, the infrastructure, so that product teams, they just focus on building the product and they focus on figuring out whether the product makes sense, iteration, velocity of that. And the side effect of that is that the same product may be able to just run this as is in different app or different platforms. So we have people building for Android maybe, and then they pull that experience to VR or iOS, vice versa. It may not be the same exact code, but the portability of expertise help developers really move fast in the company.
Awesome. Like I can totally see that as a Meta engineer, like people jumping over between boundaries. This is so amazing, really. I want to hear also a little bit from Alfonso at Coinbase. How has React Native impacted productivity of your engineers?
Of course, yeah. Between let's see. So besides the feature parity that Kevin mentioned, and I think one key point is that if your company was already using React, for example, then obviously most of the engineers working in, like, say, web can learn easily to go into mobile, and then you have a lot of resources that can move around. That's like the promise from React, right? Or React Native. Something very powerful that we found was you can, since most of the changes or most of the features that we make are in JavaScript, and it's slow to build React or like native apps locally, we can leverage that and use or cache the native builds. And so it has increased our productivity by a lot just by caching native builds, and just our engineers will just download that native build and just compile TypeScript, which is way faster. And anyway, that's
I can totally relate to that. I've been working as an Android engineer for like 6 or 7 years, and the speed boost you get from not building native every time is just like incomparable. So I can totally see how that impacted you. I want to ask the same questions also to Caliph, and specifically, I know Microsoft has a solution called Code Push that allows to deliver updates over the air. So I'm wondering, like, no one has mentioned this yet. I suppose this has improved your productivity at Microsoft, but can you tell us to which extent, Caliph?
Yeah. So we have Code Push is one of the technologies, but there's also a few others that we have internally. But the general idea is that it allows us to push, like bits in real time over to user machines that are running our products. And the fact that we switched over to React Native and that we had a stable, interface between our experiences and the products, they allowed us to rev both of them independently. And what we do often is when we're running experimentation, for example, we can push different versions of those JavaScript bundles over to different users. That has allowed us to decrease our delivery time for new features or experiments significantly, like in the order of I think in the case of Xbox, for example, it would take them about more than a month to release new versions of the whole native stack, and they could release React Native experiences to Xbox applications within about 10 minutes. So in production, so that was a pretty significant boost to our delivery mechanism.
And that's awesome to hear, especially if you consider like the user, like the size of the user base that you folks have at Microsoft is really impressive to hear.
Yeah.
So we do have some live questions, and I'm leaning towards prioritizing those just to make the conversation a little bit more like spicy and live. So quick reminder for everyone, make sure you write your questions there. I will be picking them first. And you can also upvote messages. So if we start having more, we will be answering first the one that receive more votes. So the first one is from Jatin. I hope I pronounced your name correctly, which is, do you guys use Jetpack Compose and Swift UI in your native modules in React Native? Who wants to take this one? Kevin, I believe you have some insights on this, right?
Yeah, definitely. So Swift UI and Jetpack Compose provide a lot of different different APIs, kind of similar to React. So we did some research back in the day just to understand like what is the internals a little bit, and then we actually did some experiment or exploration on like how easy is it to create a integration, like as if it's a Jetpack Compose component or Swift UI component. So at least for Jetpack Compose, it was somewhat possible. We didn't really pursue into the very great detail. It's more about like understanding our limits in the React Native framework and understanding how easy it is to integrate like a different rendering engine. So yeah, it is possible. We just don't use it within the core. It is an option of for people who would like to explore that as well.
Got it. We do have another question, which is somehow like directed to folks at Meta, and I will keep on asking you, Kevin. And this is a bit spicy. Like I've been asked these same questions multiple times, but I really want to hear your thoughts. Which is like, why was a Threads app not built with React Native?
Yeah, excellent question. At Meta, we believe that products, teams, or organization, they have their own priority. They have their own choice of tech stack. Instagram have a lot of underlying infra they have built for many years. Organization who built the new app will need to decide, okay, what is the best use of the infra for that specific product. So I'm not involved in any of the development of Threads. What I believe is that using the same principle, using what allows their engineer to be more productive at that moment for the product needs is probably the best call for a product. So the answer really, it depends on the use case. And I was thinking to talk about that later on the topic of like what to choose. And then I think the answer, it depends, right? I think organization will have constraints, expertise, or other priorities that might, play into this decision making. So that's what I would say.
I can totally relate on that. It depends is my favorite answer. I think is the classical engineering answer to like those, open-ended questions. I actually want to give a shout out like to Expo. If you folks in the audience are new to React Native, make sure you check out Expo. Is a framework to create React Native apps. And like if your use case is prototyping something, like Expo is the best tool. Like I was impressed by seeing how quick I am by just using tools like that one. But there might be other scenarios where like React Native is not the best solution. So it really depends on what you have to build. So we have another question from the audience. I see now questions are starting to flow, which is something that I really love. It's from Mo, and he or she asks how to make sure that there are clear boundaries between different workflows on a large-scale project with different teams working on it. I'm not entirely sure what you mean here with workflows, but I suppose you work in a big code base with multiple teams collaborating on different features, and how do you make sure that the monorepo or the repository where you work is properly structured so that folks can collaborate and don't step on each other's shoes? So the question is more like organizationally, folks, how do you organize your work? I'm curious to hear from folks. Like I'm sure folks at Microsoft have. I remember seeing this constellation of different monorepos to make code sharing possible. I don't know if Caliph, you have insights to share here.
Yeah, I mean, I can talk a little bit about some of the experiences that we've had. So we we have multiple repos within Microsoft, and one of the challenges that we faced was that we had folks who were building experiences that they wanted to port to different applications as seamlessly as possible. So think of it as an example. Like we have features where you can see the contact information of people, their ID, their email address, their organizational chart, and things like that. And those experiences are useful in Teams, in Outlook, in other apps like other Office apps. So we had a challenge where when people were building those experiences, they tried to port it to different apps, they were missing functionality. Like an API was available in one application, it wasn't available in another, and that created a lot of friction for seamlessly implementing these. So one of the things that we did was just try to come up with a shared SDK that was an SDK that was agnostic of the application. So you could call into it, and then within the application that you're going to call, we will provide the specific implementation for it. That allowed people to move their experiences quickly between those applications. We also built, like generic test apps that could live in any of those repos, so that at the very least you had the ability to test your experience once before you migrate it over. So that's one of the ways that we did handle the problem of multiple repos within our organization.
Awesome. Shout out to React Native Test App from you folks at Microsoft. I know a lot of libraries have been using it to sort of make sure that the library works with all the various React Native releases. It's such a great tool. Thanks you folks for investing on it. So I'll jump over on another question that we have prepared, but I again invite everyone to send live questions over. We're gonna pick the next one from the live chat. What I want to ask is, what is the biggest challenge your organization has faced when you consider adopting React Native at scale? We know there are like big topics in the React Native ecosystem, like big challenges that every company experience to some extent. So I'm curious to hear your specific story, like what was the biggest, I don't know, pushback, or like the biggest challenge, like the biggest project that you have to face when dealing with React Native. Mustafa, how about you tell us a little bit from Shopify?
Sure. So the biggest challenge that we faced was not technical. It was more of a culture and people issue. We've spent like years building a really strong native team, and we had like really strong native engineers who had spent years building that expertise, and having everybody take that, but also then start learning a new technology, a language, and a framework was there was a good amount of pushback around that. But the way that we overcame was that, like, I think React Native, this was around 4 years ago. So back then, React Native had, like, people had preconceived notions about React Native, about what's possible, what's not, what the performance is like. So we encourage everybody to try it out instead of just relying on blog post on the internet or what they heard from their friends or anything like that. Just like give it a shot and have everybody build some apps in React Native on the side, and then try to make it easier for them to adopt React Native. A lot of like friction was around like, okay, I have to spend a lot of time to learn this new technology, but what if we made it super easy for you? Like you go through this one course and you know everything you need to know to build React Native apps at scale. So once we started doing that, and also we had some issues with some performance issues, so we invested heavily in that side as well, and we built an open source some libraries for that. And after that, most of the people came on board, and now they're happily doing React Native every day.
Awesome. Thanks for sharing like your challenges. I'm curious to hear from Caliph again, like, I think you folks are like maybe also similar to us, have the biggest, diversity in terms of platforms. So yeah, like what's the scope there of the challenges you're facing?
So there was one that is very similar to what Mustafa was describing, where there's a cultural aspect and an expertise aspect that influences the decisions that people take when they pick a platform. In some cases, we had people who just heard about React Native, wanted to get going on it pretty quickly, and they were productive quickly. In some cases, we had native developers who, like really wanted to access the native code and found the JavaScript layer to be a hurdle for them. They didn't enjoy the experience as much. What we did in our case was we also tried to build very easy to get started experiences. So like think of if you're building Office, for example, internally within Microsoft, you have a way where you can very quickly just get a Hello World application stood up. You clone a repo, you build it. There's a task pane that gets created. Your Hello World is there. You open VS Code, you start coding, you can change things very quickly, and you get an experience up and running. So we tried to reduce that barrier to entry as much as possible to allow people to prototype and see what they feel about the experience. And in practice, we see that there's a good amount of people who take a dependency on React Native after that. There are others who will choose to stay either with native because they may have libraries that exist already, or they feel the experience allows them to just stay native and build, let's say, on Android and iOS separately. Or we have people that will use web views as well for other reasons. But in general, we found that when it comes to like helping people adopt React Native, just the ability to get them started quickly was made a huge difference for us. I can talk about another challenge that we had, which is because of the size of the company and the fact that I mentioned earlier, we don't have mono repos. One of the challenges was that we had multiple versions of React Native being used across the company. And that became a challenge because when we had to maintain tools, when we had to share experiences across those apps, it was a challenge. So that's one thing that I'm really happy with now. When we started, a few years ago, releases were not as predictable in React Native, so we couldn't plan when to do our upgrades. But recently, it's been very, very predictable. So we know, roughly every quarter or so, there's a new version coming out, so we can coordinate an upgrade across the company, even if it's happening across multiple repos. And we've seen that be fairly successful, with most people being, at most 1 or 2 releases behind, which makes it much more easier for us to coordinate sharing our experiences.
Awesome. Thank you very much for sharing. I'm curious now to hear from Kevin. And, like at Meta, we do have this dual class of challenges, because on one hand, we have users of React Native that feels similar pain as you folks, but also we are building the framework, and the different perspective of, being the framework builder has its own category of challenges. So Kevin can speak a lot about it, I'm pretty sure, right?
Yeah, definitely. So I'm going to talk about the point of view of our org. We built this technology. So the challenge has been, how do we support thousands of developers throughout the company to enjoy the latest and greatest while innovating? So in a way, it's kind of like you change a race car when the race is ongoing, and then you need to keep everything running. So that's kind of the nature of the challenge here. There's a lot of solutions to this, and we really think hard about all the corner cases, the constraints. So it forces us to build a durable solution that works for many use cases, if not all of them. And we focus on that so that nobody else need to do that. Hopefully, all of you can enjoy the benefits the same way that our developers can benefit. So it is a lot of a constraint, and it's about prioritization, about different constraints, and then when things doesn't work, how do you do it? How do you overcome the next blocker? And all of that is part of the play.
Awesome. So talking about building sustainable architectures that work great for everyone, there is one question from the audience which I need to ask you, Kevin. It's from Mo again. And the question is, what is Meta doing to push adoption of the React Native new architecture?
Yeah, internally and externally, there are different set of strategy. Internally, we push the main Facebook app to the latest architecture, so we did that. In the new apps development or like projects on a new different part of the company, we try to push on the latest setup, just so that our team doesn't have to maintain 2 different runtime for the app, and debugging becomes easier, building product becomes less confusing. And we're providing self-service tool, wikis or guidance, so that people who have extra time, they will take their time to upgrade their apps getting support from us to like ask questions and that. And for external, we are working hard to make it available for many more people outside. And in one of the a few release in the past, like 72, and then like now soon in 73, we have a lot more new architecture layers that people can adopt. They can try it out, they can provide feedback, and then the whole point is to bring it out there with all the lessons that we have from Meta so that all of you can enjoy it as well. So yeah, we're actively working on this space, not only for internal, but also for external.
Absolutely. If I can add a couple of bits, this year has all been about backward compatibility. So if you see the features that we released in React Native 072, there is one called Fabric Interop that allows you to use old libraries with the new architecture. And similarly in 073, there is going to be more updates on this space. So we're doing, like, as Kevin said, a lot of effort in this space to push the adoption of the new architecture. I do have another spicy question. This time is not from Meta, but it's from Microsoft. So Caliph, this is on you. And folks are asking, Dev is asking, I'm curious why the projects at Microsoft are not using Xamarin, which I believe is not even called Xamarin anymore. But you can tell us.
Yeah. So it's not necessarily that everyone is using React Native. In fact, like our goal was not to make React Native the single, like cross-platform solution across the company. That would have been completely unfeasible. People actually pick the technology that's suitable for them. So we have people who are also using web views, who are using Electron. I am sure someone out there is using Flutter as well within Microsoft, but it's more. The reason people picked React Native in particular was around, like I can speak on for Office. Like the reason why we picked it for the scenarios that we did was because one, it was the familiarity of our developers with JavaScript was one of the big motivating factors. As well as Office, we cannot go rewrite Office from scratch. It just would not be practical. And so the ability to build those brownfield applications was extremely important. But also when we compared to other technologies where we could do that, React Native had very good performance characteristics for some specific scenarios that we cared about. So, like let's say we want something to display very quickly after the application boots. We found that React Native was a suitable way to do that. So it really depends on the team specifically and what they're trying to do. I think across the company we have a breadth of features that use different types of cross-platform technology. The React Native is by far one of the more popular ones.
Awesome. Thanks for clarifying. We're slowly moving towards the end of this panel. So I still want to pick from the live questions because they're really insightful. So there is another one, which is from Dev, and he asks other panelists, what is the benefit of using React Native other than other competitors, so other cross-platform solution? Mustafa, you seems to have some insights on this from Shopify. Have you considered using Flutter or Kotlin multi-platform or web-based solutions? What's your take?
Yeah, there are a bunch of different advantages. We use Kotlin multi-platform as well, but it's for places where it makes more sense. But for React Native in particular, we evaluated a bunch of different options, and the things that stood out for us were two things. One is you don't have to learn a completely new language to start building using React Native. If you're familiar with JavaScript and TypeScript, you can get started, and the learning curve is not too steep. So there's that. The other reason is that you don't have to go all in. You can adopt it piecemeal. So if you have a well-established native app, you can just build a single feature using it and then see how it works and then scale it up if you want to. So that makes the transition much smoother versus dropping everything and trying something new altogether.
Awesome. I see in the chat there are also questions related to Kotlin multi-platform taking over React Native. What's your take on that, Mustafa?
I think it's a very interesting technology. It's a different approach to doing cross-platform development. I also happen to be on the Kotlin Foundation, so I work with that technology as well. But I think The biggest advantage for Kotlin multi-platform, in my opinion, is like if you have a lot of native code already and you want a way to share it with another platform, let's say you have a bunch of Android code that you want to share with iOS, Kotlin multi-platform is a decent way of doing that. But I think React Native also has its own advantages. Like UI is way easier in React Native, and you can just build once and runs everywhere. So at the end of the day, like my thoughts about all of this is that these are all tools in your toolbox, and you have to pick what works best for you in whatever problem you're trying to solve.
Awesome. So as we are really close to the end of this panel, I want to wrap up with one final question. Like I want to collect your wisdom and advice for folks that are willing to start considering using React Native at scale, as we all do. And the questions from Nate was a live question. Is as someone just getting into React Native and developing hybrid for iOS and Android, what are 3 things that you recommend we keep in mind as we get started? I would love everyone to answer. It might not be 3 things, it might be just one. So whatever, folks, you are free for all. I will say I will start with Kevin from Meta. Maybe you can give us some insights or suggestions, and all the other folks will follow through.
Yeah, at least my experience and the experience of the org has been you need to focus on what your organization needs. Maybe you want to build something very rapidly. Maybe you want to focus on the polish and stuff. A lot of that has parts into the decision making. And one thing is about having the native engineers, because the strength of React Native is the ability to jump into the native platform when you need to. You may not need the same number of native expertise, but having some of them will help. And then once you have the good foundation, you can scale your team and add it, finding the React developers. So again, it depends on the needs, but then the key is that being flexible and allowing people to jump into the native stack if that's what you need.
Awesome. So we go next to Alfonso. Like, what's your take?
Sure. Yeah, no. As we've said here, React Native is very powerful. It allows you to do over-the-air updates, do cross-platform features. I think I have maybe 2 recommendations. One is leverage state-of-the-art tools like Expo, which are very helpful even in the beginning. And to complement what Kevin was saying, React Native, it's still in its core, it's still native. So still invest in native expertise. And that's it.
Awesome. So up next, we have Mustafa from Shopify. Some experience or learnings or takeaways?
Yeah, for sure. So 2 things I would say I'd recommend companies potentially adopting React Native at scale. One is invest heavily in training. Don't rely on like people going through blog posts and learning things on their own. Just make it easier for people to learn React Native, and it will make everybody's life so much easier. The other thing I would say is invest also very heavily in the developer experience. Make it so easy to adopt React Native that it should be a no-brainer. And once you do that, you just removing friction goes a long way when you're trying to make a shift like this.
Awesome. And Caliph, you have the honor to wrap up this collective wisdom around React Native.
Sure. Yeah. So I would say, I think, I'll echo some of the things that's already been said. I think it's really important to understand if you're trying to build it at scale and you will have developers of different backgrounds, it's really important to understand that background, because the unique needs that they will have is different. Like native developers will be very happy to quickly bridge to native code if they need to write modules that they are going to use. JavaScript developers might find this a little bit more challenging, and even if they can do it, it's not going to lead to a good developer experience for them. So knowing like who you're actually targeting makes a really big difference. In our case, we have a platform team that helps with that. So when we have people who are pure JavaScript developers, we provide them the libraries that they actually need, and that helps them be successful. The other thing I would say is we mentioned Expo, but in general, once you're getting ready to use React Native, like just learn about the richness of the overall ecosystem. because there's a lot of libraries out there. There's a lot of tools that you can leverage that will get you started very quickly, and that you don't have to rebuild yourself. So it's another thing that I would recommend people to do.
Awesome. Thank you very much for sharing so much. I think before we actually call it a day, it might be worth to share some references for the folks. Like, I see there are more questions coming through. If people are interested in getting in touch with the React Native community, what would be your go-to destination? I can definitely mention that the React Native website is reactnative.dev, and we are quite active on the GitHub issue tracker for React Native. But do you folks have recommendations on like communities or forums that you would recommend for folks to look into if they have like more questions or doubts related to React Native, and so they can get them answered?
We run a Discord group for React Native at Shopify, which is open to the public. You can find links for that at the Flash List GitHub page, and we are in there helping people who are using our React Native open source libraries. But anything else with React Native we'll try and help with that as well.
Awesome. Alfonso, Caliph, do you have other resources to share?
Yeah, so I think for us, we're also pretty active on the GitHub repos that we own. If you ask questions there, we'll be happy to respond. We also have a Twitter feed, React Native MSFT. You can connect with us there as well. I think this would be the main ones.
Awesome. Okay, folks. I want to thank you very much for being with us on stage today.
Thank you.
Thank you.
And I also want to thank everyone in the audience for being live. I hope you really enjoyed the panel, and I hope to see you all at the next Mobile at Scale conference.
Perfect.
Welcome back, everyone. Hope you enjoyed lunch and the fantastic panel discussion. Mobile development can be tricky because of things like connectivity, latency, and coordination, which is why experimentation is really important in today's product world. Now let's hear from Ben Bader, a senior staff software engineer at Instacart. Ben will unravel the fascinating journey of how a return to the fundamental principles of computer science empowered Instacart to construct a mobile AV system capable of scaling to serve millions of devices. Ben will also talk about the problems they faced while making it. Ben, go ahead.
Hello, my name's Ben. I'm a software engineer at Instacart, and I've been working here for about 5 years. Before that at Microsoft, before that at a whole bunch of other startups for the past decade at least. And I've divided my time in my career mostly between mobile and back-end development. Today, I want to talk about experimentation, how Instacart developed the ability to run tens of thousands of experiments for millions of shoppers and customers with billions of assignment decisions every day. I'm going to talk about the system we built, which is called Roulette. I'll spend a few minutes describing how we built it, why we built it, and how it works. I'll spend a little more time talking about how the things that made it really work well on the back end didn't work very well on mobile, and how we had to turn the system kind of upside down to fix that. At the end of this talk, I'm hoping to leave you with some ideas for developing your next system and for how to bridge the gap between the systems that back-end developers build and things that mobile developers need. So let's begin. To set the stage, Instacart is, what is it? It's an online grocery technology company. We founded in 2012, went through Y Combinator, grew a whole bunch, and now we're available to 95% of the households in the US and Canada. So on top of the delivery business, we also run ad services for over 6,000 consumer packaged goods brands. So what is experimentation? What does that mean here? So experimentation can mean a lot of things. I like GitLab's definition the best here. They call it a way to validate and measure improvements to a digital product against particular goals. So experimentation is critical for the way we operate. Whenever we're facing a product design question or a business question, we want to be data-driven. We want to be informed. And experimentation is the best tool we have for informing ourselves. Obviously, you can't measure everything that matters, and you can't use experimentation to replace critical thinking and your own judgment, but it remains an essential tool. So how do we get here? Well, how did we arrive at this place where we needed to build the system that I'm talking about? In the beginning, in 2012, as most companies at the time did, we had a single Rails app with a single Postgres database on Heroku. We had a rudimentary experimentation system built on an open source library called Flipper, and honestly, it worked really well until around 2016. Around then, we'd outgrown Heroku, moved to AWS, and our monolithic code base became too unwieldy to keep working, so we refactored it. One app became 2, became 4, and even more. And each app got its own copy of an experimentation system. Each app got its own team with its own mission. And as those teams progressed, their needs diverged, and the systems they used to run experiments diverged too. Around 2018, we had settled in with about 4 major monolithic applications and a whole constellation of smaller services, each with their own mutually incompatible experiment systems. Like we couldn't even run an experiment across 2 of them at the same time. And this state of affairs continued until around early 2020 when we started the Roulette project. So what is Roulette? Roulette is an assignment engine. Let's talk about some terms here. So what is an assignment engine? That's a weird term. An assignment engine is a system that assigns users to a variant of an experiment. When I talk about experiments, I mean specifically multivariate experiments in which groups of users or a cohort are shown a variant, a different user experience, and then we track the behavior of those users through time to see what impact to the business those different user experiences might have had, or as this is commonly known, A/B testing. Except in this case, we often have more than just A and B. So when we kicked off this project, we had to decide what we wanted it to do. So obviously we wanted it to be a single source of truth because the problem was that this is pure chaos. Like if we wanted to run an experiment from a customer placing an order all the way through a shopper fulfilling it, we're a host. There's no way we could have done that. So we needed a single source of truth with a single service vending the same experiment data to everybody. We wanted it to be correct, which sounds kind of trite to say, but some systems do compromise on consistency or correctness in order to prioritize availability. We can't make that trade. One user has to see one variant for one experiment. Otherwise, our experiments lose their power. And since it's a new service, we wanted it to be fast, couldn't introduce too much latency. One problem that we had was that even though we couldn't do experiments end to end, we had a lot of experiments running. Some of our most common endpoints might have dozens of experiments running at the same time. If we had a separate network call for each of those experiments, we would have completely blown our performance budget for the whole request already just an experiment assignment. So we had to be smarter than that. So how do we hit that target? So it turns out that the cheapest network call is no network call, and the cheapest assignment that we can do is no assignment. We had our assignment service do nothing except for tell all of our applications what experiments were in force. And all of the assignments were actually done in process in the applications that needed them, where and when they needed. So this actually had some important implications. So if all of our applications are generating assignments by themselves, they're not coordinating with anything, that means assignments need to be a deterministic process. They have to have the same answer every time. Secondly, the fact that we're not consulting some central authority for assignments means that there's no state. And that means that assignment is not only deterministic, but it is a pure function. It can only consider the experiment definition itself and whatever attributes of the user are relevant to that experiment. So this is what we built, and we shipped it, and we found out that not only did it meet our latency goals, it actually crushed them. We watched the tail latency at the P90 for our experimentation systems. All the existing ones dropped from like tens of milliseconds to single-digit microseconds. Great success. It introduced a new problem, which was, since our applications are the ones doing the assignments, like how do we keep them informed? Like how do we keep them up to date? It's actually an important problem. We'll talk a little bit more about that later. First, I want to talk about the roulette data model, how it works and why it works, because it's interesting. So the central data structure in roulette is called a feature definition, or feature for short. The salient aspects of it has a name, like it's a unique name to identify the experiment, has some variants that it knows about, and it has rule sets. What's a rule set? A rule set has rules, which are predicates about a user, like is the user an admin, or is this customer shopping at a particular set of retailers? They define what segment of traffic the experiment applies to. And finally, they have variant weights, like what proportion of the experiment population should get a particular variant. So when a prospective cohort member satisfies all the rules for a rule set, then they are assigned a variant according to those weights. And how this assignment process happens is key to the system, and it's worth spending a little bit of time talking about. So the nature of variant assignment in experiments is that it must be unpredictable. Like if you can predict the variant of a user before you actually assign it, you introduce bias to an experiment, you erode its or completely eliminate its predictive power. So cool, most of the time that's easy. You just like slap a call to random and it's fine. But the problem for us is that as a distributed and stateless and uncoordinated system, we can't actually use a random number. Otherwise, nobody would agree on the same assignment. So we had to be a little smarter. What could we do? Well, backend devs are probably nodding along here. They see where it's going because, as in so many other problems, the answer involves hashing. Hashing is, of course, the process of converting some arbitrary data into a fixed width byte string with the properties that that output is usually unique to the input, and crucially, it's unpredictable from the input. So it's randomized, in other words. There are thousands of hashing algorithms out there you probably know, like SHA-1, SHA-256, MD5. We settled on one called XXHash. It's small, it's super fast, it's high quality, it's available everywhere, basically. And so with this, we can take something unique about an experiment, like its name, and something unique about the user, like an ID or an email address, combine them and get a randomized number that is nonetheless deterministic. And this is enough to get predictable randomized variant assignment. Like a simple thing to do is just take that number, mod the number of variants you have, and boom, you've got a variant ID. Almost. So for one, if you're thinking about modular bias, yeah, we're thinking about this too. This is not the final solution. And it's not the final solution for another reason. As we just talked about, variants have weights. Like they're not just evenly distributed. We need to be able to accommodate like 5% of people go into control, for example. So how can we do that? Is there any way we can adapt this technique for weighted variants? Well, it turns out that yes. One simple thing we could do is just pad the list of variants. Like say A, B, and C variants have weights of 2, 1, and 1. Well, we can just keep the same algorithm, but just put A in that list twice. That by itself is enough to get predictable, randomized, and weighted variants. But it's still not quite enough. Because while this works in isolation, the fact is experiments exist in time and they change over time, particularly when you take into account optimizations like multi-armed bandit. I won't talk too much about how those work, but the salient aspect of those is that bandit and other techniques involve looking at experiment data as it comes in, analyzing and identifying which variants are performing better than the others, and directing a greater share of traffic to the winning variants. And in this way, you minimize the loss or maximize the gain from any particular experiment. Well, that means we need to be able to change the weights dynamically. And that poses a problem here because in this algorithm, changing the weights is destabilizing. It re-randomizes everybody's variant, which effectively destroys your experiment. So what we want is, if we're going to emphasize variant A, de-emphasize variant B, the only motion that we want to see users going from B to A. Can't do that with this approach. It just fundamentally won't work. So what can we do? I think some backend engineers probably see where this is going too, because this turns out to be a classical problem in storage and networking domains. And the classical solution is something called consistent hashing. There are a number of different algorithms out there. The one we settled on is called weighted rendezvous hash. For me, this is like a desert island algorithm. It does so much with just a very small amount of effort. It's fast, it's simple, and really useful. I won't get into too much detail about how weighted rendezvous hash works, other than to say it sort of adapts existing hashing algorithms. So we can take XX hash and plug it into this formula and get a score adjusted by weight. If you want to learn a little more about it, I would really encourage you to go follow the link on this slide because it's an easy read and really enlightening. Okay, so now that I've talked a little bit about how roulette works and why it works, let's talk about what the system looks like. What does it look like? It looks like this. So this diagram shows all of the major components of roulette as it exists today at Instacart. Up here is a database-backed RPC service. It has a small number of components do a small number of things. It's basically a very simple wrapper around our source of truth, which is a single Postgres database that holds all experiment definitions, past and present, because key thing about that is that it's append only, which will be a little important later. And next we come to the heart of the system, which is the backend client libraries. These are much more complex than the backend itself because they do the work. Most of their complexity is in the assignment evaluation algorithm, which I'm not going to get into right now. But the libraries are interesting from a scalability perspective. Remember that they have to hold all of the experiment set in memory and keep it up to date. How they do that dictates a lot of the backend's performance and even its design. So we had a couple choices here. Mobile developers are familiar with polling versus push notifications. Polling is when you reach out to a backend service on Cadence and say, hey, what's new? Push notifications, in contrast, are when the server itself reaches out to the clients and says, hey, I've got something new for you. Please go get it. Of the two approaches, push notifications are much more scalable. They're much more efficient. But they're also a lot harder to build, so we didn't do it. We went with polling, and it's not optimal, but it's been good enough for the past few years. So the only reason that this works at our scale, well, okay, what's our scale? Right now we have about tens of thousands of experiments running at any given time that the libraries need to know about. So that means that our compressed data set is probably in the megabytes at this point, the tens of megabytes even. And so our libraries poll for updates every 30 seconds. If we weren't smart about this, that means we're shipping 10 megabytes to every application server every 30 seconds. And you very quickly reach a point where this is just not operable. It's too expensive. It's too slow. We're wasting too much bandwidth. We're wasting CPU resources. So this is where the append-only nature of our database comes to the rescue. Because every change to our database results in inserting a new row with a new auto-incremented ID, we have a very natural high watermark that we can use. So we use this to introduce pagination to the API. Whenever Roulette sends down a response, it includes that high watermark with it. Clients can include that value the next time they make a request, and the server can say, here's what's new since the last time you made a request. And that actually works very well. It makes operating Roulette possible. And in fact, it made it super efficient because almost all of the responses that happened after we introduced pagination were 0 bytes, which was great, super efficient, right? Like we can scale down. We don't need 100 Roulette nodes. We maybe need 3. But this introduced an interesting problem in the nature of bimodal responses. What does that mean? So the vast bulk of our responses were 0 bytes long, which is awesome. But a small portion of our responses were many millions of bytes. And that usually happens when an app starts up for the first time and has no experiment data at all, and it needs the whole data set. So this combined with auto-scaling in a really interesting problematic way. So because the vast majority of our responses were so tiny, we could auto-scale down very easily to like 3 nodes. Problem being when we lit up a major new customer internally. When the morning scale up happened, when our traffic started to spike up early in the morning as people began to place orders, we very quickly had this wave of worst case requests and a skeleton crew of roulette servers to handle them. So this situation actually caused several hours-long outages. Eventually, we solved it by just eliminating bimodality entirely. So one of my favorite questions to ask when it comes time to design a system is, does it need to be, how reliable does it need to be? Does it need to be as reliable as S3? If the answer to that question is yes, the next question is, can we just use S3? In this case, the answer to both is yes, we can. So we can just keep a cache of up-to-date feature definitions in S3. So whenever a new application node starts up, instead of asking the roulette backend for that worst case request of all the data, it can just download it from S3. This means even if roulette's completely down, an app can start up and have a reasonably up-to-date experiment set. And since we introduced this, we haven't had a single scale-related outage. S3 is pretty amazing. Next, I'll talk about the events pipeline just a little bit. I won't spend too much time on it, except to note that despite all the talk about statelessness of the system, the entire point of an experimentation system is to keep state, right? Like we go to all this trouble because we want to know who saw what, when, and why, so that we can analyze their impact on the business. Like that's the whole point. You can build this on basically any streaming platform today. Like we've used Kinesis and Kafka at different points. They all work and there's not much to it. And finally, we come to the newest member of the family, the mobile SDKs. Instacart is a mobile-first product, and so our mobile developers naturally want to take part in the same experimentation ecosystem as their back-end counterparts. And here is where the nature of mobile applications comes into play. So up to this point, Roulette had only ever had back-end customers. And as a consequence, a lot of our design hinged on these kind of unstated assumptions that we made about how things work. Mobile applications being so different, this posed quite a challenge to us. So what were those assumptions and how were they problematic? We assumed that memory was cheap and freely available. You can hold all this data in memory all the time without impacting your host application. We assumed that bandwidth was capacious and widely available, that we could download as much data as we need whenever we need to. Laughably untrue on mobile. And finally, we assume that services are available, that once we boot it up, we can reliably talk to anything we want to talk to whenever we want to. And if you've ever used your phone in a grocery store, you know that's not true. So what did we do about it? The first challenge we had to tackle was bandwidth usage. So we are available to 95% of households in the United States and Canada. That's a very broad geographic footprint, and mobile availability is really variable across that space. So, 5G is great, but it's not as widely deployed as we'd like. A lot of our customers are still stuck on LTE or 4G even. And bandwidth is really expensive, right? Like customers pay by the gigabyte. And when your payload is in megabytes, it doesn't really take very many polling requests before you start hitting people in their wallets. And that's just unconscionable. Like we couldn't ship a product that would cost our customers money that way. So right away, we hit this impasse. So what can we do? It seemed like everything that made Roulette successful on the back end, not only was it ineffective on mobile, it was actually a liability. So what could we do? Well, remember when I talked at the beginning about how we had to turn the system on its head to make it work for mobile? Well, that's where this happens. We ended up re-centralizing all of the logic. Instead of having smart clients at the edge, we had dumb clients, and we centralized all the assignment logic in a back-end service. So let's talk a little bit about why that was a reasonable thing to do. So for one, the bandwidth usage. So an evaluation object, which is the data structure that's produced by computing a variant assignment, is much smaller than an experiment definition. Not only that, it has an incredibly regular structure, which means it compresses beautifully. Like we usually see maybe 95% or more bandwidth savings when we enable compression. So that's great, saves our customers some money. This is less mobile specific, but this has the additional benefit of keeping the number of SDKs that we have to a minimum. So remember that I showed you we have 3 backend SDKs. Each one implements its own copy of the assignment evaluation algorithm, which is quite complex. Keeping these 3 in sync is a tremendous amount of work, because if they get out of sync, typically the result has been subtle bugs that take a long time to discover, cause a lot of damage until they're fixed. This also has the additional benefit of helping with availability. So this is really kind of the key problem for mobile experimentation systems, bandwidth aside. Operating conditions for mobile applications are just so diverse. Like, you really can't make many assumptions about the environment your apps are going to be used in. Particularly, you can't assume good or even any network access. Well, we can't eliminate the need for network access, but we can minimize it by saving the assignments to disk. It sounds simple, and it is simple, but it worked. So on Android, we use SQLite, which was a dream. It makes inserting and querying for your assignments super easy. Even that might have been overkill, though, because our iOS team just decided to dump the whole blob to disk and read it out when they needed to. It worked. So this fixed the availability problem, but introduced a bit of a race condition. So the first time you start up an app, after installing it, you have absolutely no experimentation data whatsoever. And I hope it's clear at this point in the industry that blocking app startup by fetching multiple megabytes of data from a remote server, it's not a great thing to do. In fact, it's something to avoid at all costs if possible. Well, we didn't really solve that problem. We hacked around it. If the app needs an experiment assignment before it has the data, we just assume that it's in a control variant and call it a day. We do save that override locally so that we have a consistent user experience, but it works. And it also has the nice effect of solving the memory issue. Since we're saving things to disk and reading them out as needed, we don't need to keep all that data resident in memory. So that memory is available for the application to use for actually useful things. And with that, that brings us up to today. So it's not all sunshine and roses. Although Roulette serves us very well at scale, there's a lot more work to do. I think one of the biggest problems that we have to solve right now is the API that we expose to people. The Roulette architecture itself is fairly simple, but the data structure is quite complicated, and exposing it in an API has been challenging. The problem is that because experiment definitions are so flexible, you have all those rules that can require different bits of input about a user, developers really have no way of knowing ahead of time what input they need to provide. So it's very easy to have a misconfigured experiment. I think what we need to do is find out some kind of opinionated APIs that give safeguards. Some of our teams have built those opinionated APIs for their own environments where it works for them. I think if we want to make people successful, that we need to really think about how we approach this kind of problem in a different way. I think maybe code generation would be a really great solution here. Like, you have all these experiment definitions, so just generate a strongly typed API that people can use with confidence, or maybe even delete the backend and just check all your experiment definitions into Git and code gen off of that. Probably won't do that just for the operational overhead. Like, nobody wants to wait for CI for their experiment toggle to take effect. But we're still thinking about this. I've talked a little bit about how having multiple different SDKs is just a lot of opportunity for subtle bugs. We'd love to consolidate this into a single code base. And there's a lot of good options nowadays. We could write something in Rust or in Kotlin native, or even, honestly, even C++ would be a tremendous improvement. We haven't done this yet just for resource constraints, but I would love the peace of mind this would bring. And I think finally, the last important thing we want to do here is reevaluate our decision to use polling everywhere. It's worked, but it is inefficient. I'd love to take advantage of Firebase or APNS to push updates out to our mobile clients. I would love to do something similar on the backend, like set up RabbitMQ or something to fan out updates to all of our backend nodes. That would be awesome. But that's to be determined in the future. And with that, I want to say thank you. At this point, I've talked about how Instacart developed the ability to run tens of thousands of experiments with billions of evaluations every day. I've talked a bit about how it works on the back end, and I've talked about how what makes things work on the back end doesn't necessarily translate to mobile and how you have to reconsider. I've talked a little bit about how a small amount of computer science can have a tremendous impact and how even more of our problems are just solved with duct tape and glue, and that's fine. So I hope that I'm leaving you with some ideas for your next system design, or at the very least, with some problems that you'll know how to avoid before you encounter them. And with that, I just want to say thank you for spending your time with me. It's been a pleasure.
Thank you, Ben. As we finish our presentations today, get ready to learn about Meta's impressive UI design systems. Join Meta software engineer Aaron Kotlin as he talks about the tools and infrastructure Meta is working on. He'll also show us how they use common building blocks in different design systems and apps to make them work better. Aaron, take it away.
Welcome. I'm super excited to talk about the work we're doing on multiple design systems across apps at Meta. I'm Aaron, and I'm a software engineer at Meta. And I want to be super upfront that all the work we'll be talking about today is a product of a bunch of different folks across a bunch of different roles and teams here at Meta. Before we get into it, let's take a quick look at the agenda for what we'll be talking about today. We're going to start with some background on what are design systems and why are they useful. Then we'll jump into how we're building the foundations for those design systems. Then we'll pivot a bit into how we're using all the work that we're doing to ship large-scale UI updates to users faster. And then finally, we'll jump into a topic that's a lot newer and more experimental on how we're building chameleon components. So before we get to the exciting parts of the talk, let's go through a quick background. What are design systems? Design systems are a collection of design decisions and principles which apply to a product or a group of products. Bored? Confused? Me too. So let's take a look at what a design system is in terms that actually make sense. A design system is made up of three things. The first thing is foundational elements, things like colors, fonts, spacing, and much more. The second are reusable UI components, things like text, button, profile photo, and other elements that are used over and over again throughout an app. The third is design principles. These are the set of instructional guidelines and patterns for how those first two things should be used. These give people a set of rules to follow for how to apply those foundational elements and components throughout a product. So now that we have a high-level understanding of what a design system is, why would we use it? What's it useful for? The first main benefit of design systems is branding and consistency. The design system is what allows us to take brand elements and bring them to life through those foundational elements, baking the brand into our product through things like typography scales, color palettes, and branded headers. A prime example of this is the recognizable Facebook blue. Design systems also bring consistency to the product. By repeating the same colors and typography styles and components and patterns throughout the app, users become more familiar with it and it allows them to predict and understand the UI better. Another benefit is quality and accessibility. Design systems raise the bar for quality, with built-in considerations for things like accessibility, usability, and performance. Designing color palettes which meet color contrast guidelines, building reusable UI components which are accessible, and addressing performance directly in those components allows us to solve these problems once and get benefits across the product. The final benefit of design systems is speed. At a product-wide level, having all aspects of a design system collected in one place helps us test and release design language updates at scale faster than we otherwise could. And at an individual team or feature level, having this reusable system reduces the sheer volume of individual design decisions needed to build a product. Teams working on something like Marketplace can focus on making design decisions for their product, rather than rebuilding things like buttons and colors over and over again every time. So let's take a look at the landscape of design systems in the industry. A typical approach is a company which has a single app with a single design system. An example of this is Spotify's Encore design system. And this is the case for the vast majority of companies. But there are a few companies out there who have more than one app. So let's talk a little bit about what happens in that case. One example of a company with many apps is Google's G Suite, which uses its Material design system, which Google has actually open sourced. You can see that they're applying the same design system to many apps, giving them all a similar look and feel, which creates that feeling of a suite of apps. At Meta, our approach is having multiple design systems across our apps. And we use this approach to differentiate products and create unique experiences for users across those apps. The Facebook app has FDS, the Facebook design system. Instagram has IGDS, the Instagram design system. WhatsApp has the WhatsApp design system. Messenger has MDS, the messenger design system. And these are just the major ones. We also have design systems for things like VR experiences, cross-meta experiences, and many, many more design systems. So if a single design system is made up of foundational elements, components, and design principles, what happens when we have over 20 of them? All of a sudden, it's an overwhelming amount of things to support. And now we've reached the part of this talk where we can talk about design systems at scale. Having over 20 design systems is a lot, but keep in mind that the choice is intentional. For today's talk, we won't focus too much on the existence of so many systems, and our goal isn't to consolidate down to a single system. Rather, we want to figure out how to sustainably support the 20 plus design systems we do have at Meta. So how do we do that? By building a porch. Okay, so we aren't actually building a porch, but you can think of what we're building like one. We're building the design systems platform, which is the foundational layer for design systems. This is like the deck of the porch. Then on top of it, every design system at Meta can come and define themes, which are like the columns of the porch. And finally, we can build chameleon components, which are like an awning on top of the porch, providing value to all of the design systems. So back to our porch. Let's talk about the deck. The design systems platform is the deck of our porch. When we built design system components in the past, we often hard-coded the style values, like in this code snippet. This makes it super fast and easy to build new components, but it presents a huge problem for keeping these components consistent, especially across multiple platforms, iOS, Android, web, and designs in Figma. You can see that the height value here is set to the number 44, corner radius is set to 8, and the background color is set to FFFFF, the color code. Now, design systems are using design tokens. As you can see in the highlighted changes, we've replaced those hard-coded values here with things that look like variable names. These are known as design tokens. Rather than referencing a concrete value in the component, we reference a token name instead. And somewhere down the line, this name gets resolved into a real value. You can think of a design token as essentially just a key value pair. The advantage of using design tokens is that they decouple the design decisions from code. Rather than having those hard-coded values and having to update them across multiple platforms and places, we can consolidate everything, using the same token name everywhere and storing the value in a centralized place that propagates down to all the platforms. And the way we're doing that is using Design Systems Platform, which is a home for the foundational elements of design systems. It's a central infrastructure for those foundational elements that can be used by any design system at Meta. We're representing foundational elements with design tokens for things like colors, typography, size, spacing, and more. And the result of this is that we're creating UI consistency and efficiency for design and engineering teams by having to make updates once. We're automatically syncing those token values to code and to Figma. So at a high level, here's what the platform actually looks like. You can see on the left that any design system can define tokens in JSON using the W3C draft specification. We have jobs which observe changes to those tokens and to the JSON and trigger code generation to all of the different frameworks and platforms that a design system might want to target: iOS, Android, React Native, designs in Figma, web. And then finally, teams are able to use those tokens within their product code. And every design system benefits from onboarding. Design Systems Platform is generic enough to support any design system on any platform or UI framework. The foundational elements like colors and typography are now working the same way across apps and design systems where it's possible, which wasn't the way it was before. Secondly, design systems are getting the benefit of speed. By automatically syncing the tokens to code and design, we're saving time, and it makes it easier for design systems to expand to a new framework or platform. And finally, the third benefit is that consistency we've been talking about. By defining values in one place and syncing them to all platforms, we don't have to worry about having different corner radii across the different platforms, or different colors or typography across the different platforms. So DSP is a really strong foundation to build on. It provides a lot of value on its own for individual design systems. But the main benefit is that now we can go and we can build additional capabilities on top of it. And the first of those is theming. Theming is like the pillars of our porch. Every design system can use theming to build their own pillar. And the reason why we need themes is because historically, shipping large-scale UI updates has been slow. Apps like Facebook evolve a lot over time. You can see the difference between 2013 and today here. And while this evolution takes place over many years, there's often big moments where we want to ship large-scale UI updates or refreshes all at the same time. And theming is what makes those UI updates faster and easier. Since we've decoupled the design decisions from the component implementation using design tokens, we can leverage that to greatly improve our iteration speed. You can see on the left in the example that we have a theme provider wrapped around the button component, which was in the example earlier. The theme provider tells us to use the square buttons theme. And by using a different theme provider around our component hierarchy, we can read different values for the tokens and modify the UI. In about 5 minutes, I spun up this example on the right of the production Facebook Android app using square buttons instead of the usual round buttons. And there's a lot of real-world examples of how we're using theming to ship these UI updates. One example is global margins in Facebook. Another is changing the navbar font to our custom FB Sans font. And the final one is updating marketplace tiles, trying a bunch of different variations between the classic marketplace look and feel and other variants which have rounded edges and gutters. Theming allows us to shorten the iteration cycle. We're able to ship design updates to users faster, meaning we can deliver a more modern and easy-to-use experience. For teams at the company, we're spending less engineering time to ship these design changes, and more of the effort is spent focusing on the design changes themselves and tweaking the themes to find the best experience. Additionally, theming enables us to have more effective testing. Using theming, we can spin up a bunch of different variations of a UI and play around with the look and feel until we arrive at the best one. And we can refine those. By having that volume, we can do user research, A/B testing, and continue to test out the product until we land on the optimal UI that's the best experience for everyone. And what does that look like in practice? Using theming is not too different than using tokens. The steps in the code are largely the same. The first step is to define a theme, which extends the default theme and overrides the values it wants to change. So for the example from a few slides ago with the square buttons, all I had to do was extend the default theme and change the corner radius values for our button component. The second step is for our code generation jobs to run and generate the theme and token code. You can see here an example of the generated code for that square buttons theme that I'm talking about. You can see that the overridden values are defined, but all other values are simply resolved using the default theme. And the final step is what we saw earlier, wrapping a UI or component hierarchy in a theme context provider, which tells all the UI within it which theme it should use to resolve values. So getting into a bit more about resolving those values, what does that actually look like? When we only had tokens, it was as easy as looking up the value within the default theme. But now that we have theming, we have another level of abstraction that we need to deal with. The first step is to figure out which is the active theme. And then the second step is to ask that theme to resolve the token name into a value. On the screen, you can see a quick diagram of what this looks like, as well as some sample code for how resolving a color token would work. So at this point, we've talked about how every design system at Meta can utilize design tokens and theming through our common infrastructure, design systems platform, in order to deliver better experiences to users faster. That's great for helping individual design systems scale. But what about how we help the company scale its efforts better across multiple design systems? That's what we're doing with our Chameleon component library. We spent a while talking about the foundational elements of every design system, things like typography and colors and how they can be represented with design tokens and theming. But now we're going to pivot into the other major aspect of design systems, which is UI components. And these Chameleon components are the awning of our porch. They're providing a layer across all of the pillars and providing value for all of them. So taking a step back to design systems. If every design system has a component library, and we have more than 20 design systems at Meta, that means we have more than 20 component libraries. And each of those component libraries consists of a fair number of components, anywhere from 15 to 60, if not more. And then each component needs to be built on every platform or framework that the design system supports. This usually means at least iOS, Android, and web. So if you crunch the numbers, that comes out to a ton of components, easily 500 or more. And each component isn't cheap. For every component we build, we need to solve for things like usability. Are our components easy to understand and interact with? Accessibility. Do we have screen reader support, meet color contrast standards, and much, much more? And quality on the whole. Lots of other fundamental quality aspects like performance, right-to-left text, truncation, and translations. And at the end of the day, most of these core components are fundamentally similar across design systems, although they do have some differences. Let's take a look at a few of the components we have and how they look across a few design systems at Meta. Here's button, for example. Profile photo. Text input. And the list goes on and on. So what if we could build a single component library that supports many design systems? That's exactly what we're doing. We're building chameleon components, which change their appearance to match the host app and look like the design system of that app. This work's super new and exciting, but it also means everything I'm presenting here is totally subject to change as we continue to evolve our solutions in the space. Thinking about the chameleon components, there's two main challenges that we see. The first is differences in component functionality. You can see on the top here that the FDS list cell supports a title text, a subtitle text, and then an even smaller meta text, whereas the XMDS list cell on the bottom only supports a title and a subtitle. Another challenge is in restricting property types and enforcing design system rules and constraints. For example, an FDS button should only take in FDS colors or FDS icons, whereas an Instagram button, an IGDS button, should only take in IGDS colors and icons. It would be pretty weird if you were in the Instagram app and suddenly everything was looking like Facebook colors and Facebook icons. So it's important that we enforce these restrictions at the component level. But unfortunately, tokens can't solve these problems. Tokens and theming alone are great for a single design system, but they don't provide an overarching solution when we need multiple design systems to be supported at the same time. Different design systems have different sets of tokens, different constraints, and different rules, which can't be done by tokens alone. So we're building variants, which power our chameleon components. Variants, also known as component variants, are an abstraction layer built on top of tokens and theming, which allows different design systems to work together in a single component. You can think of variants as a contract between the design system and the component style. And this isn't a new concept. We borrowed this concept from the existing design idea, and it maps fairly one-to-one. We're just encoding it technically. So what even is a variant? Variants provide a schema of configurable style properties for a component. For something like a button, it's the text color, the background color, the text style, the border, all of the aspects which are configurable in terms of the style of a component. You can see in the graphic here an example of a primary button, a de-emphasized button, and a secondary button. These are 3 examples of variants for a button, and each of those configurable properties is filled by a token. And the variants are directly a part of our component API. So you can see for our button component, variant is a prop, which is currently being passed in as a FDS button variant of the type secondary and the size small. So people are directly using these in the component API. And how that actually works is that variants are producing style values for the component to render. So we receive something like that FDS button variant with the secondary style and the small size. We get it as a bucket of FDS tokens, which we then resolve using the themes for FDS into actual primitive style values which a component can render. And a huge win of this is that the resulting component implementations are completely devoid of design system code. Our button component doesn't need to know anything about FDS, or IGDS, or MDS, or any of the other design systems. By resolving the variant into a collection of style values, we simply apply those raw style values to the component, meaning that our component is entirely focused on rendering the style values. And back to the two challenges we were talking about earlier, variants allow us to solve both of them, enforcing design system rules and accounting for differences in functionality. The FDS button variant, for example, only takes in FDS colors, and it only takes in FDS icons, and we can enforce this via type checking at the variant level. For more information on how the variants are actually working, there's a blog post coming out as well, so I encourage you all to take a look at that. So the advantage of these chameleon components is that we're solving for quality and accessibility in one place, and every design system at Meta is able to reap the benefits. So to wrap up, we've covered a lot of different areas we're working on to make design systems successful at Meta. We talked about the strong foundation we're building and how tokens enable a single design system to scale to many platforms and keep consistency across them. We talked about the pillars we're building, theming, and how it allows a design system to deliver a better experience to users faster. And we talked about the awning, our future-focused work on chameleon components, and how it enables more efficient investment in component libraries. I'm super excited about where we're going from here, and I hope you found this helpful. Thank you.
Thank you so much, Aaron, for sharing your insights into Meta's design systems. Today at Mobile at Scale, we had the pleasure of exploring various aspects of mobile development through a variety of presentations and discussions. As we look ahead in mobile development, we see exciting changes on the horizon. This field is becoming even more important as our primary way of interacting digitally. We're also excited about upcoming trends in mobile architecture, open source projects, and improvements in the developer experience. I love how the mobile development community is always pushing boundaries and shaping the digital world. And I want to thank you from the bottom of my heart for being a part of today's event. I'm looking forward to the exciting developments that will fuel our discussions in the coming year. Be sure to check out our upcoming events, Video at Scale in November and Winter Systems at Scale in December. You can register to join, and don't forget to subscribe to the At Scale mailing list for the latest news. Thank you again for being here with us today.